12 miles across. That's smaller than Manhattan. But inside this tiny sphere lurks the most terrifying object in the known universe. A magnetar contains more mass than our entire sun, crushed into a space you could drive across in 20 minutes. Its magnetic field could erase every credit card on Earth from halfway to the moon. One sugar cube of its material weighs as much as Mount Everest. When it gets angry, it releases more energy in 1/10 of a second than our sun produces in 100,000 years. If you enjoy learning about these cosmic monsters, hit that like button and subscribe for more mind-bending space content. Prepare yourselves. We begin our journey into the impossible. 25 times more massive than our sun, a giant star reaches the end of its life in the constellation Cassiopeia. For millions of years, this stellar behemoth has been locked in an epic battle between two fundamental forces. Nuclear fusion pushes outward with the power of billions of hydrogen bombs exploding every second. Gravity pulls inward with crushing, relentless force. Today, gravity wins. The star's core runs out of fuel in less than a second. Without the outward pressure from fusion, gravity collapses 20 solar masses worth of matter into a sphere just 12 miles wide. To understand how extreme this compression is, imagine taking every single person on Earth and crushing them into a space the size of a marble. Now, multiply that by a trillion. The collapse happens so fast that the outer layers of the star don't even know what's happening yet. They're still falling inward when they smash into the newly formed core at 30,000 miles per second. The collision creates a shockwave that rips through space with the power of 10 billion suns. But something strange happens during this cosmic catastrophe. The collapsing star had been spinning slowly, maybe once every few days. As it shrinks, the laws of physics demand that it spins faster, like a figure skater pulling in their arms. The dying star's rotation accelerates to hundreds of times per second. The magnetic field, already strong enough to lift a battleship from across the solar system, gets compressed along with everything else. When you crush a magnetic field, it doesn't just get smaller, it gets exponentially stronger. The star's original field strength multiplies by millions. In the span of 10 seconds, what was once a star bigger than our entire solar system becomes a magnetar. A neutron star with a magnetic field so powerful it defies human comprehension. The field strength reaches 100 million billion times stronger than Earth's magnetic field. If you place this object at the distance of our moon, it would strip the iron from your blood. Scientists first discovered these monsters in the 1970s, when Soviet spacecraft detected mysterious bursts of gamma radiation. The signals were so intense, they overwhelmed every detector on both Venus probes. For years, nobody knew what could produce such incredible outbursts of energy. The truth turned out to be far stranger than anyone imagined. Only about 30 confirmed magnetars exist in our galaxy out of billions of stars. They represent the most extreme outcome possible when a massive star dies. Most stellar deaths produce regular neutron stars or black holes. But when conditions align perfectly, the right mass, the right rotation speed, the right magnetic field strength, Fe, nature, creates something far more terrifying. These cosmic beasts live fast and die young. Their incredible magnetic fields contain so much energy that they literally tear themselves apart over 10,000 years. During their brief lifetimes, they randomly erupt with violence that can be detected from billions of light years away. The magnetar's surface temperature reaches 18 million degrees Fahrenheit. That's 3 times hotter than the core of our Sun. But this heat isn't left over from the star's death. The magnetar generates this temperature continuously by converting magnetic energy into thermal energy. It's literally cooking itself from the inside out. Inside this cosmic pressure cooker, matter exists in states that cannot be reproduced anywhere else in the universe. The interior contains phases of matter so exotic that physicists are still trying to understand what's possible. Some regions may contain free quarks, the fundamental particles that normally remain forever locked inside protons and neutrons. But understanding what happens inside a magnetar means taking a journey into realms where the normal rules of physics break down completely. What we discover there will challenge everything we thought we knew about matter, energy, and the limits of reality itself. The battle that creates a magnetar begins 10 million years before the star dies. Deep in the core of a massive star, nuclear fusion burns hydrogen into helium, releasing energy that keeps gravity at bay. But fusion is a losing game. Every second, the star burns 4 million tons of hydrogen, gradually building up heavier elements in its core. First comes helium, burning at 100 million degrees. When the helium runs out, carbon ignites at 600 million degrees. Then, oxygen at 1 billion degrees. Each new fuel burns hotter and faster than the last, but also runs out quicker. The star becomes like a cosmic onion, with shells of different elements burning at different temperatures. Silicon burning represents the final stage. At 3 billion degrees, silicon nuclei smash together to create iron. But iron refuses to fuse. Unlike every element before it, iron actually absorbs energy when forced to combine with other nuclei. The moment iron appears in the core, the star's fate is sealed. Iron accumulates in the center like ash in a fireplace. When the iron core reaches 1.4 times the mass of our Sun, something catastrophic happens. The temperature and pressure become so extreme that iron nuclei can no longer maintain their structure. Protons and electrons get crushed together to form neutrons. This process releases a flood of particles called neutrinos that escape from the core at the speed of light. In 1 second, more neutrinos blast out of the dying star than our Sun will produce in its entire 10 billion year lifetime. The neutrino flood carries away so much energy that the core's temperature drops instantly. Without thermal pressure to resist gravity, the iron core collapses faster than a falling bullet. In 0.6 of a second, matter denser than an atomic nucleus compresses into a sphere 12 miles across. The density becomes so extreme that a teaspoon of this material would weigh 6 billion tons on Earth. The collapse stops only when the neutrons themselves refuse to be compressed further. Neutrons are held apart by something called degeneracy pressure, PIE, a quantum mechanical effect that prevents identical particles from occupying the same space. This creates the most rigid substance possible in our universe, but the collapsing outer layers don't know the core has stopped. 20 solar masses of stellar material continues falling inward at 25,000 miles per second. When this avalanche of matter hits the solid neutron core, it bounces back like a rubber ball hitting concrete. A shockwave explodes outward through the falling material. For 8 hours, this shockwave struggles to escape the star's massive gravitational pull. Normally, the wave would stall and collapse back inward, but neutrinos streaming from the core give it just enough extra energy to break free. The outer layers explode into space as a supernova, visible from billions of light years away. But the real show is happening in the core. During the collapse, conservation of angular momentum spins the neutron star up to incredible speeds. A star that once rotated every few days now spins hundreds of times per second. The magnetic field, frozen into the collapsing plasma, gets compressed by a factor of 1 trillion. If the conditions are exactly right, if the rotation speed falls between 100 and 1,000 revolutions per second, if the magnetic field exceeds certain critical thresholds, a dynamo effect kicks in. The spinning, conducting neutron fluid generates additional magnetic field through a process called the magnetohydrodynamic dynamo. This amplifies the already enormous magnetic field by another factor of 1,000. The result is a magnetar with field strengths reaching 100 trillion times Earth's magnetic field. Only 1 in 10 supernovas creates a magnetar instead of a regular neutron star. The universe has just given birth to the most dangerous object possible without creating a black hole. Picture the exact moment when physics breaks. It happens 1 second after the stellar core begins collapsing, when protons and electrons can no longer exist as separate particles. The temperature reaches 100 billion degrees. The pressure exceeds anything found elsewhere in the universe. In this hellish environment, the fundamental forces that govern matter are about to rewrite themselves. Under normal conditions, protons and electrons maintain their distinct identities through electromagnetic force. Electrons orbit protons in neat, predictable patterns that have remained unchanged since atoms first formed. But inside a collapsing stellar core, these rules no longer apply. The pressure becomes so intense that electron clouds collapse directly into atomic nuclei. Electrons get squeezed into protons with such force that they combine into neutrons, releasing a burst of neutrinos. In less than 1 second, every atom in the core disappears. 20 solar masses of ordinary matter transforms into something that has never existed anywhere else. This isn't just compression. This is the complete reorganization of matter at its most fundamental level. What emerges is neutronium, a matter composed almost entirely of neutrons packed together, like cosmic ball bearings. The density reaches 500 trillion grams per cubic centimeter. To put this in perspective, imagine compressing all the mass of every human being on Earth into a sphere the size of a sugar cube. But neutronium is just the beginning. As the collapse continues, even stranger things happen. The intense magnetic field creates conditions that would be impossible to achieve in any laboratory. Photons, all particles of light, begin splitting into pairs of particles and antiparticles. The vacuum of space itself becomes polarized, acting like a crystal that bends light in impossible ways. At magnetic field strengths above the quantum critical threshold, atoms can no longer maintain their normal spherical shape. Instead, they stretch into thin cylinders, becoming 200 times narrower than normal but maintaining the same mass. If you could somehow observe hydrogen atoms in this environment, they would look like microscopic needles. The magnetic field becomes so strong that it affects the fabric of space-time itself. Einstein's equations predict that intense magnetic fields should warp space and time, creating regions where the normal geometry of the universe breaks down. Inside a magnetar, space becomes twisted into complex shapes that mathematicians are still trying to understand. During these critical first seconds, the neutron star settles into a layered structure unlike anything else in the cosmos. The outer crust consists of atomic nuclei in a crystal lattice, surrounded by a sea of free electrons. But these aren't normal nuclei and neutron-rich isotopes that would instantly decay if they existed anywhere else. Deeper inside, atomic nuclei begin to merge into increasingly exotic shapes. Scientists call this region nuclear pasta because the nuclei form structures resembling spaghetti, lasagna sheets, and hollow tubes. Each shape represents a different balance between nuclear forces and gravitational pressure. The transition from crust to core happens gradually over a distance of just a few hundred yards. But crossing this boundary means entering a realm where the distinction between individual particles begins to blur. Free neutrons start to flow like a superfluid, with zero resistance to motion. In the very center, conditions become so extreme that neutrons themselves may break apart into their constituent quarks. This creates a soup of fundamental particles that exists nowhere else in the observable universe. Some theoretical models suggest that stranger forms of matter might form, particles containing strange quarks that make the material even denser and more exotic. The entire process, from stellar collapse to stabilized magnetar, takes less than 10 seconds. But in those 10 seconds, nature demonstrates that the universe contains possibilities far beyond human imagination. The magnetar is complete. Now the real fireworks begin. Imagine Manhattan compressed into a sphere 12 miles across, but instead of buildings and people, it contains the mass of 1.5 suns. This is the scale of a magnetar, an object so dense that 1 tablespoon of its material would outweigh Mount Everest. but calling it simply compressed matter misses the truly bizarre reality of what lies inside. The magnetar's structure resembles an onion made of increasingly exotic materials. The outermost layer forms a solid crust about half a mile thick, composed of atomic nuclei arranged in a perfect crystal lattice. But these aren't ordinary atoms. The intense gravitational field creates nuclei with extreme neutron-to-proton ratios that would be completely unstable anywhere else in the universe. Near the surface, nuclei like iron 56 exist in relative normalcy, but as you descend through the crust, the nuclei become increasingly neutron-rich. Iron 70, iron 80, iron 90, isotopes that would decay in microseconds on Earth remain stable under the magnetar's crushing pressure. The crystalline structure creates the hardest solid material known to exist. This crust is 10 billion times stronger than steel, yet it must constantly adapt to the magnetar's changing magnetic field. When magnetic stresses exceed the crust's incredible strength, the entire surface can crack in an event called a starquake. Below the solid crust lies the inner crust, where matter enters a regime never before seen in nature. Atomic nuclei become so neutron-heavy that they begin leaking neutrons into the surrounding space. These free neutrons form a quantum fluid that flows through the lattice of nuclei with zero resistance. The neutron fluid behaves as a superfluid, a state of matter that can flow through the tiniest cracks without friction. This superfluid can rotate independently of the solid nuclei, creating internal friction when the magnetar's rotation changes. Scientists believe this interaction between superfluid neutrons and solid nuclei causes the timing glitches observed in pulsar signals. Descending deeper, the nuclei themselves begin to change shape under the extreme pressure. Instead of maintaining their normal spherical form, they stretch into tubes, sheets, and complex geometric structures. Physicists nicknamed these configurations nuclear pasta because they resemble spaghetti, lasagna, and other familiar shapes. Gnocchi phase nuclei form spherical clusters. Spaghetti phase nuclei stretch into long rods. Lasagna phase nuclei flatten into sheets separated by layers of neutron fluid. These exotic structures exist in a zone where nuclear forces and gravitational pressure achieve a delicate balance found nowhere else in the cosmos. At about 5 miles below the surface, even these strange nuclear configurations give way to something more fundamental. The boundary between atomic nuclei and free neutrons disappears entirely. Matter becomes a uniform fluid of neutrons, protons, and electrons, the core of the magnetar. In this core, neutrons flow as a superfluid, while protons form a superconductor with zero electrical resistance. The combination creates conditions perfect for sustaining enormous electrical currents that generate the magnetar's incredible magnetic field. These currents can flow forever without losing energy, maintaining field strengths that would be impossible to achieve any other way. Some theoretical models suggest the very center of a magnetar might contain even more exotic matter. At densities exceeding 10 times normal nuclear density, neutrons and protons might dissolve into their constituent quarks. This would create a quark soup containing up quarks, down quarks, and possibly strange quarks, a state of matter that existed only briefly after the Big Bang. The temperature throughout this city-sized ball of exotic matter reaches 18 million degrees Fahrenheit. But this isn't heat left over from the supernova. The magnetar continuously generates thermal energy by converting magnetic field energy. The process heats the entire neutron star from the inside out, making it glow with high-energy X-rays. Every cubic inch of a magnetar's interior contains more energy than humanity has ever produced in its entire history. And we've only just begun to explore the mysteries hidden within. Take every magnet on Earth, every refrigerator magnet, every medical MRI machine, every magnetic levitation train, every industrial electromagnet ever built, combine their magnetic fields into one super powerful magnet. Now multiply that field strength by 1 billion billion. You're still not even close to the magnetic field strength of a magnetar. A magnetar's magnetic field reaches 100 million billion times stronger than Earth's magnetic field. To put this in perspective, if a magnetar were placed at the distance of our moon, its magnetic field would be powerful enough to strip the iron from every molecule in your body. From 600 miles away, the magnetic forces would kill you instantly by disrupting the electrical activity in your brain and heart. But these numbers, staggering as they are, barely hint at the true strangeness of magnetar magnetism. At these field strengths, the universe itself begins to behave differently. The magnetic field becomes strong enough to affect the quantum vacuum, the supposedly empty space between particles. Virtual particle pairs that normally appear and disappear without effect become influenced by the intense magnetism. The vacuum becomes birefringent, like a crystal that splits light into different colors depending on its polarization. Photons traveling through this magnetized vacuum experience something that should be impossible. They can split into two separate photons, or merge with other photons to become gamma rays. Light itself becomes unstable in the presence of such extreme magnetism. The magnetic field also warps atoms into unrecognizable shapes. Hydrogen atoms, normally spherical clouds of electron probability, stretch into thin cylinders 200 times narrower than normal. The magnetic force overwhelms the electromagnetic force that normally determines atomic structure, creating atomic needles that exist nowhere else in the universe. Even more remarkably, the magnetic field stores an enormous amount of energy, more energy than our sun will produce in its entire 10 billion year lifetime. This energy exists in the form of magnetic field lines that twist and tangle through the magnetar's interior and surrounding space like cosmic spaghetti. The source of these incredible magnetic fields remains one of the greatest mysteries in astrophysics. During the stellar collapse that creates a magnetar, magnetic field lines become frozen into the conducting neutron fluid. As the star shrinks from thousands of miles across to 12 miles across, the magnetic field gets compressed by factors of trillions. But compression alone cannot explain magnetar field strengths. Something else must amplify the magnetic field during or shortly after the neutron star's formation. The leading theory involves a magnetohydrodynamic dynamo, ATF, a process where the spinning, conducting neutron fluid generates additional magnetic field through electromagnetic induction. For this dynamo to work, conditions must be exactly right. The neutron star must rotate between 100 and 1,000 times per second. The initial magnetic field must exceed certain critical thresholds. The temperature and electrical conductivity must fall within narrow ranges. Only about 1 in 10 supernovas produces these perfect conditions. The magnetar's magnetic field isn't uniform like the simple dipole field of Earth. Instead, it forms a complex, twisted structure with multiple poles and field reversals. Hotspots form where magnetic field lines penetrate the surface, creating regions that glow millions of times brighter than the surrounding crust. These hotspots can move across the magnetar's surface as the internal magnetic field evolves. When two hotspots merge, they release enough energy to outshine entire galaxies for brief moments. The merger creates a burst of X-rays and gamma rays that can be detected from billions of light years away. The magnetic field also creates powerful electric currents in the magnetar's magnetosphere, the region of space dominated by its magnetic influence. These currents accelerate charged particles to near light speed, creating beams of radiation that sweep across space like cosmic lighthouses. The magnetar's magnetic field represents the ultimate expression of one of nature's fundamental forces. But this is only the beginning of the magnetar's assault on the laws of physics. At the moment, a magnetar's magnetic field strength crosses the quantum critical threshold. Reality itself begins to malfunction. This threshold calculated by physicists as 441 billion Gauss, represents the point where quantum mechanics and electromagnetism collide in spectacular fashion. Beyond this limit, the universe enters uncharted territory, where the normal rules simply stop working. The quantum vacuum, which we think of as empty space, turns out to be anything but empty. It seethes with virtual particles, electron-positron pairs, that pop into existence for brief moments before annihilating each other. Under normal conditions, these quantum fluctuations happen so quickly that they have no observable effect on the world around us. But a magnetar's field changes everything. When virtual particles appear in a magnetic field stronger than the quantum threshold, they become influenced by the magnetism before they can disappear. The magnetic field polarizes the vacuum, causing it to behave like a birefringent crystal. Light traveling through this polarized vacuum splits into two different modes, each traveling at slightly different speeds. This effect, called vacuum birefringence, means that a magnetar literally changes the properties of empty space around it. X-rays and gamma rays, traveling through the magnetar's magnetosphere, experience delays that depend on their energy and polarization. The magnetar creates its own version of cosmic slow motion, where different colors of light travel at different speeds. Even more dramatically, photons with enough energy can spontaneously split into electron-positron pairs when traveling through the magnetized vacuum. This process, impossible under normal conditions, becomes commonplace near a magnetar. High-energy gamma rays cannot maintain their existence. They immediately convert into matter and antimatter particles. The reverse process also occurs. When electrons and positrons collide in the intense magnetic field, they can merge into a single high-energy photon instead of the usual two lower-energy photons. The magnetar's field strength is so intense that it fundamentally alters how light and matter interact. The magnetic field also affects the geometry of spacetime itself. According to Einstein's general theory of relativity, intense electromagnetic fields should create gravitational effects. The magnetar's magnetic field contains so much energy that it contributes measurably to the object's total mass and gravitational pull. Current theoretical models suggest that magnetic field lines near a magnetar become so twisted and tangled that they create regions where space curves in complex ways. These magnetic flux tubes can trap light and matter, creating invisible highways through space where particles follow predetermined paths, regardless of other forces acting on them. Near the magnetar's surface, magnetic field lines emerge from the crust at specific points called magnetic poles. But unlike Earth's simple north-south dipole field, magnetars often have multiple poles scattered across their surface in complex patterns. Field lines connect these poles in intricate networks that shift and evolve over time. When magnetic field lines reconnect, ND2, suddenly changing their configuration, they release enormous amounts of stored magnetic energy. These reconnection events can heat plasma to temperatures of billions of degrees and accelerate particles to nearly the speed of light. The energy released during a single reconnection event can exceed the total energy output of our Sun over thousands of years. The twisted magnetic field creates a magnetosphere extending thousands of miles into space around the magnetar. Within this region, charged particles become trapped along magnetic field lines, spiraling back and forth between the magnetar's magnetic poles. These trapped particles form a kind of magnetic bottle that can store and channel enormous amounts of energy. The magnetosphere also creates dead zones where matter cannot exist in normal form. Any atom entering these regions gets stretched beyond recognition or torn apart entirely. Electrons get forced into quantum states that would be impossible to achieve in terrestrial laboratories. Scientists have detected evidence of these extreme magnetic effects using space-based X-ray telescopes. The polarization and energy distribution of X-rays coming from magnetars show clear signatures of vacuum birefringence and other quantum electrodynamic effects. The magnetar has turned its immediate cosmic neighborhood into a laboratory for testing the most extreme predictions of theoretical physics. The magnetar's outer crust appears deceptively simple, a thin shell of crystallized atomic nuclei covering the exotic interior. But this crust represents the strongest solid material that can exist anywhere in the universe. It's 10 billion times harder than diamond, yet it lives under stresses that would shatter continents on Earth. When this ultimate material finally breaks, it releases energy that can be detected across the entire galaxy. The crust extends from the magnetar's surface down to about half a mile deep, where matter density reaches 100 million grams per cubic centimeter. At this depth, atomic nuclei become so neutron-rich that they start leaking neutrons into the surrounding space. But in the outer regions, nuclei maintain their distinct identities arranged in a perfect crystal lattice. This crystalline structure forms under conditions that would be impossible to reproduce anywhere else. The gravitational pressure compressing the crust exceeds the pressure at Earth's core by factors of billions. Yet the crystal maintains perfect geometric order across distances of miles, creating the largest single crystal structures ever formed. The magnetic field threads through this crystal lattice like cosmic rebar, providing additional structural support while simultaneously creating enormous internal stresses. The field strength varies by factors of millions across different regions of the crust, creating pressure gradients that would instantly vaporize any terrestrial material. As the magnetar ages, its magnetic field slowly evolves and changes configuration. Field lines twist and untwist as electrical currents deep in the core shift over time. These changes propagate upward through the neutron star's interior, eventually reaching the solid crust, where they create mechanical stress. The crust can withstand stresses equivalent to supporting the weight of Mount Everest on every square inch of surface. But eventually, the accumulated magnetic stress exceeds even this incredible strength limit. When the breaking point is reached, the crust doesn't crack gradually, it fails catastrophically. A magnetar starquake begins when a fault line develops somewhere in the crystal structure. The initial crack might be only a few inches long, but it propagates across the magnetar's surface at nearly the speed of light. In milliseconds, fracture lines spread across thousands of square miles of surface, releasing stresses that have been building for years. The energy released during a major starquake defies comprehension. The December 27th, 2004 eruption from magnetar SGR 1806-20 released more energy in 1/10 of a second than our Sun produces in 100,000 years. The burst was so intense that it temporarily blinded every X-ray and gamma-ray detector in the solar system. This starquake cracked the magnetar's crust across an area larger than North America. The fracture shifted the surface by several feet, a tiny distance by human standards, but enormous for an object where matter is compressed to nuclear density. The sudden rearrangement of mass changed the magnetar's moment of inertia enough to alter its rotation period permanently. When the crust cracks, it doesn't just release mechanical energy. The breaking crystal lattice severs magnetic field lines that have been locked in place for years. These field lines carry enormous amounts of stored magnetic energy that gets released instantaneously when the structural support disappears. The liberated magnetic energy heats the fracture zone to billions of degrees, creating a fireball of plasma that erupts from the magnetar's surface. This plasma expands at significant fractions of light speed, carrying magnetic field lines along with it. The expanding fireball shines with the brilliance of 10,000 suns, emitting primarily X-rays and gamma rays. The starquake also launches seismic waves through the magnetar's interior. These neutron star earthquakes travel through matter so dense that their speed approaches significant fractions of light speed. When seismic waves reflect off the boundary between the crust and core, they can trigger secondary fractures and additional energy releases. Most remarkably, starquakes can change the magnetar's magnetic field configuration permanently. The crustal fracture allows magnetic field lines to reconnect in new patterns, sometimes creating additional magnetic poles or shifting the location of existing ones. The crust that protects the magnetar's interior can become its most dangerous weapon. Below the crystalline crust lies a realm where individual atoms cease to exist. Here, in the magnetar's inner crust and core, matter exists as a fluid of pure neutrons, protons, and electrons, the fundamental building blocks of atomic nuclei, liberated from their normal constraints. The pressure in this region exceeds anything found elsewhere in the observable universe, creating conditions where the distinction between liquid and solid becomes meaningless. The transition from solid crust to neutron fluid happens gradually over a distance of a few hundred yards. As you descend through the inner crust, atomic nuclei become increasingly neutron-rich until they can no longer hold their excess neutrons. These liberated neutrons form droplets, then streams, then rivers of quantum fluid that flow between the remaining nuclei. At the crust-core boundary, roughly 5 miles below the surface, the last atomic nuclei dissolve entirely. What remains is uniform neutron fluid, with a sprinkling of protons and electrons maintaining electrical neutrality. But this isn't ordinary fluid like water or oil. This is a quantum fluid where the neutrons behave collectively as a single, coherent system. The neutron fluid flows as a superfluid with exactly zero viscosity. Unlike normal fluids that gradually slow down due to friction, superfluid neutrons can flow forever without losing energy. They can squeeze through gaps smaller than atomic nuclei and flow up walls in defiance of gravity. In a magnetar's core, this superfluid neutron component comprises roughly 90% of all matter. The remaining 10% consists of protons and electrons that form their own exotic quantum states. The protons, under the intense pressure and temperature conditions, transform into a superconductor, a state where electrical current flows with absolutely zero resistance. These superconducting protons can carry enormous electrical currents that persist indefinitely, generating the magnetic fields that make magnetars possible. The pressure at the magnetar's center reaches 100 billion pounds per square inch. To visualize this pressure, imagine the weight of the entire Atlantic Ocean balanced on a postage stamp. Under these conditions, neutrons get packed together so tightly that they actually touch each other, something that never happens in normal atomic nuclei. When neutrons are compressed to this density, they begin to exhibit collective behavior that has no parallel in terrestrial physics. The neutron fluid can support waves and vibrations that travel at significant fractions of light speed. These neutron sound waves carry energy and information through the magnetar's core in ways that solid materials simply cannot match. The boundary between superfluid neutrons and superconducting protons creates one of the most unusual interfaces in nature. These two quantum fluids can rotate independently of each other, creating internal friction when the magnetar's rotation rate changes. Scientists believe this friction explains the sudden glitches in timing observed from some pulsars. The magnetic field penetrates this neutron soup in the form of quantized flux tubes, microscopic whirlpools of magnetic field that thread through the superfluid like cosmic spaghetti. Each flux tube carries exactly 1 quantum unit of magnetic flux, and millions of these tubes must be present to account for the magnetar's enormous field strength. As the magnetar spins, these flux tubes get dragged along by the moving neutron fluid, but the superconducting protons can pin the flux tubes in place, creating tension between the two quantum components. When this tension becomes too great, flux tubes suddenly break free and relocate, causing observable changes in the magnetar's rotation and magnetic field. Temperature control in the neutron soup occurs through a delicate balance between heating and cooling processes. The decay of the magnetic field continuously deposits energy into the fluid, heating it to tens of millions of degrees. But neutrino emission from the core carries away energy at an enormous rate, providing a cosmic refrigeration system. The neutron fluid also supports exotic excitations that have no counterpart in normal matter. Collective oscillations of the entire fluid can store and release enormous amounts of energy, potentially contributing to the violent outbursts observed from magnetars. Deep within this neutron soup, nature demonstrates that matter can exist in states barely imaginable to human experience. At the very center of a magnetar, 10 miles below the surface, lies a sphere where the normal rules of physics break down entirely. Here, matter density reaches 5 to 10 times nuclear density, conditions that push theoretical physics beyond the boundaries of current understanding. In this core region, neutrons and protons may no longer exist as distinct particles, dissolving instead into a soup of fundamental quarks that hasn't been seen since the first microseconds after the Big Bang. Nuclear physics tells us that protons and neutrons are composite particles made of smaller constituents called quarks. Under normal conditions, quarks remain permanently confined within protons and neutrons by the strong nuclear force. No amount of energy can liberate a quark in ordinary circumstances. They're locked in place more securely than any prison could hold. But the magnetar's core changes everything. At pressures exceeding 10 to the 35th power pascals, ATA, a number so large it defies human comprehension, the boundaries between protons and neutrons begin to blur. Individual particles lose their identity as the strong nuclear force becomes overwhelmed by pure gravitational compression. Quarks, normally held captive within nucleons, find themselves free to roam through the magnetar's central regions. This creates a state of matter called quark soup or strange matter, depending on which types of quarks are present. Up quarks and down quarks, the normal constituents of protons and neutrons, mix freely in a quantum fluid that obeys completely different physical laws than ordinary matter. The soup may also contain strange quarks, more massive cousins, that make the material even denser and more exotic. In this quark soup, particles can transform from one type to another through processes that would be impossible in normal matter. Strange quarks can decay into up and down quarks, releasing energy that heats the core. The reverse process can also occur, with normal quarks converting to strange quarks under the right conditions. Some theoretical models suggest the core might contain even more exotic phases of matter. Color superconductivity, AS, a state where quarks form pairs similar to electrons in superconductors, could create regions with properties unlike anything observed in nature. These quark pairs might carry both electric charge and color charge, the quantum property that governs the strong nuclear force. The temperature in the core reaches 100 million degrees Kelvin, hot enough to fuse any known atomic nuclei instantly. But temperature becomes almost meaningless at these densities. The thermal energy represents only a tiny fraction of the total energy density, which is dominated by the degeneracy pressure of the quark fluid and the enormous magnetic field energy. Speaking of magnetic fields, the core region contains field strengths that approach the theoretical maximum possible in our universe. At the very center, magnetic field strength may reach 10 to the 18th Gauss, a value so extreme that it could theoretically cause spacetime itself to become unstable. The core also supports oscillation modes that can shake the entire magnetar. When the quark soup undergoes phase transitions or develops instabilities, the resulting vibrations can propagate through the neutron star at near light speed. These core oscillations may be responsible for some of the quasi-periodic signals observed from magnetars during their most violent outbursts. Rotation in the core becomes equally exotic. The quark soup can rotate independently of the outer layers, creating differential rotation that stores enormous amounts of energy. When this differential rotation becomes unstable, it can transfer energy outward through the magnetar's layers, ultimately powering surface eruptions. The boundary between the core and the overlying neutron fluid remains poorly understood. The transition from quark soup to nucleon matter might happen gradually over several miles, or it could occur in a sharp discontinuity, where the equation of state changes abruptly. This boundary region could support entirely different phases of matter that exist nowhere else in the universe. Perhaps most remarkably, the core might contain the universe's most concentrated source of dark matter. Some theories suggest that dark matter particles could accumulate in the centers of neutron stars, reaching densities where their normally elusive properties become observable. In the magnetar's core, physics enters realms where theory and observation struggle to follow. Hidden beneath the magnetar's neutron soup lies an invisible network of energy highways more advanced than anything human technology has ever achieved. These pathways, formed by superconducting protons and quantum flux tubes, carry electrical currents so powerful they could supply Earth's energy needs for millions of years without losing a single watt to resistance. Superconductivity on a magnetar operates on a scale that makes terrestrial superconductors look like children's toys. On Earth, the most advanced superconducting magnets require cooling to within a few degrees of absolute zero and can barely maintain field strengths of 20 Tesla. Inside a magnetar, protons become superconducting at temperatures of 50 million degrees, while supporting magnetic fields of 100 million Tesla. The secret lies in the extreme density of the magnetar's core. When protons get compressed to densities 5 times greater than atomic nuclei, they begin forming Cooper pairs, the quantum mechanical binding that enables superconductivity. But these aren't ordinary Cooper pairs. The binding energy between protons becomes so strong that superconductivity persists at temperatures that would vaporize any known material. These superconducting protons form a 3-dimensional network throughout the magnetar's core and inner crust. Electric currents flow along this network in closed loops that can persist for millions of years without decay. Each current loop generates its own magnetic field, and the combination of millions of loops creates the magnetar's overall field structure. The current density in these superconducting highways reaches values that would instantly vaporize copper wire. A single cubic centimeter of superconducting proton matter carries enough electrical current to power a large city. Multiply this by the volume of the entire magnetar core, and the total current flow approaches the output of entire stars. But the most remarkable feature of this superconducting network is its ability to store and transport magnetic flux in quantized units. The magnetic field doesn't flow through the superconductor uniformly. Instead, it gets organized into tiny flux tubes, each carrying exactly 1 quantum unit of magnetic flux. These flux tubes behave like microscopic tornadoes of magnetic field, threading through the superconducting medium in neat parallel arrays. Each tube is only about 10 to the minus 13 centimeters wide, smaller than an atomic nucleus, but they carry the concentrated magnetic field of the entire magnetar. The flux tubes create a kind of magnetic superhighway system. When the magnetar's magnetic field needs to change configuration, flux tubes can move through the superconductor, carrying their magnetic flux from one region to another. This flux transport allows the magnetar to evolve its magnetic field structure over time without violating the laws of superconductivity. The interaction between flux tubes and the neutron superfluid creates some of the most exotic physics imaginable. Neutron vortices, whirlpools in the superfluid neutron component, can link with magnetic flux tubes to form complex braided structures. When these linked vortices move, they can transfer angular momentum between the neutron superfluid and the superconducting protons. This coupling between rotation and magnetism may explain how magnetars can suddenly change their spin rate during outbursts. When flux tubes break free from their pinning sites in the superconductor, they can rapidly redistribute throughout the core, transferring angular momentum and changing the magnetar's rotation period by measurable amounts. The superconducting current system also provides a mechanism for storing enormous amounts of magnetic energy. Each current loop acts like an inductor in an electrical circuit, but with energy storage capacity that exceeds anything achievable with conventional technology. The total magnetic energy stored in a magnetar's superconducting current system equals the mass energy of several mountain ranges. When these current systems become unstable, they can release their stored energy in catastrophic fashion. Current loops can suddenly reconfigure, dumping magnetic energy into the surrounding matter and heating regions of the core to billions of degrees. This energy release propagates outward through the magnetar's layers, ultimately powering the violent surface eruptions that make magnetars detectable across the galaxy. The magnetar has essentially evolved into a living superconducting electromagnet powered by the fundamental forces of quantum mechanics. In the crushing magnetic fields surrounding a magnetar, the atoms that make up ordinary matter undergo transformations so radical they become unrecognizable. Hydrogen atoms, normally spherical clouds of electron probability, stretch into needle-like structures 200 times thinner than their normal width. This isn't science fiction. It's the inevitable result of magnetic forces so powerful they overwhelm the electromagnetic forces that normally determine atomic structure. Under normal conditions, atoms maintain their shape through a balance between electromagnetic attraction and quantum mechanical effects. Electrons orbit atomic nuclei in precisely defined energy levels, creating the spherical or dumbbell-shaped electron clouds familiar from chemistry textbooks. The magnetic field strength required to significantly distort these atomic orbitals exceeds anything achievable in terrestrial laboratories. But magnetars shatter these limitations completely. When the magnetic field strength exceeds 10,000 Tesla IM, already stronger than the most powerful magnets on Earth, IM, hydrogen atoms begin to noticeably elongate along the direction of the magnetic field. At 100,000 Tesla, the atoms become distinctly egg-shaped. At the million Tesla levels found near magnetar surfaces, atoms transform into thin cylinders that bear no resemblance to their original form. The transformation occurs because magnetic forces can compete directly with the electromagnetic forces that bind electrons to nuclei. In a sufficiently strong magnetic field, electrons become confined to tight spirals around magnetic field lines. Their motion perpendicular to the field gets quantized into discrete energy levels called Landau levels, while motion parallel to the field remains unrestricted. This creates atoms that are essentially one-dimensional objects, thin needles of electron probability extending along magnetic field lines. A hydrogen atom in a magnetar's field becomes 200 times longer than normal, while maintaining roughly the same total volume. The electron spends most of its time in a narrow tube around the magnetic field line, occasionally spiraling in tight circles perpendicular to the field direction. The chemical properties of these needle-shaped atoms differ dramatically from normal matter. Atomic bonds that depend on spherical electron orbitals become impossible. Instead, atoms can only bond along the direction of the magnetic field, creating chains and filaments of matter rather than the three-dimensional crystal structures found on Earth. Even more remarkably, the magnetic field affects different types of atoms differently. Hydrogen atoms, with their single electron, elongate into simple needles. But heavier atoms with multiple electrons develop complex internal structures as different electron shells respond to the magnetic field in different ways. Carbon atoms in a magnetar's field might form structures resembling molecular tuning forks, with electrons confined to multiple parallel tubes. Iron atoms could develop fan-like configurations where electron clouds spread along several magnetic field directions simultaneously. The periodic table of elements would need complete revision to account for these exotic atomic geometries. The magnetic field also affects the nuclear components of atoms. Protons and neutrons have their own magnetic moments that interact with the external field. In the strongest magnetar fields, nuclear magnetic effects become significant enough to influence atomic structure directly. These distorted atoms cannot exist in isolation. They form part of a magnetized plasma, where individual atomic identity becomes blurred. Free electrons spiral along magnetic field lines at near relativistic speeds, while atomic nuclei get trapped in magnetic bottles formed by field line convergence. The needle-shaped atoms create a medium with highly directional properties. Light polarized parallel to the magnetic field travels differently than light polarized perpendicular to it. This creates the vacuum birefringence effect that astronomers use to measure magnetar field strengths. When these distorted atoms undergo radioactive decay or other nuclear processes, the products emerge preferentially along the magnetic field direction. This creates jets and beams of particles that follow magnetic field lines, contributing to the collimated outflows observed from magnetars. The transformation of atoms into needles represents just the beginning of the magnetic field's assault on normal matter. At even higher field strengths, atoms may cease to exist entirely, replaced by exotic states of matter that exist nowhere else in the observable universe. In the magnetar's domain, even the most fundamental building blocks of chemistry bow to the supreme power of magnetism. Deep inside a magnetar, a cosmic generator has been running continuously for thousands of years without any external power source. This natural dynamo converts the neutron star's rotational energy and thermal energy into magnetic field strength. Through processes so efficient, they put human engineering to shame. The magnetohydrodynamic dynamo, operating in a magnetar's core, represents the ultimate expression of electromagnetic induction, scaled up to stellar proportions. The dynamo process begins with the magnetar's three distinct fluid components: superconducting protons, superfluid neutrons, and relativistic electrons. Each of these fluids can move independently, creating differential rotation and complex flow patterns throughout the neutron star's interior. When conducting fluids move through magnetic fields, they generate electric currents through the same principle that powers electric generators on Earth. But the magnetar's dynamo operates under conditions impossible to replicate in any laboratory. The conducting fluids have essentially zero electrical resistance, allowing currents to flow without energy loss. The magnetic field strengths reach values where the field energy density exceeds the mass energy density of the fluid itself, and the rotation rates, while slow by neutron star standards, still correspond to surface velocities of thousands of miles per hour. The dynamo's power source comes from multiple energy reservoirs within the magnetar. Rotational energy provides the primary fuel, S, the neutron star spins. Differential rotation between fluid components creates shear flows that can generate magnetic field through dynamo action. Thermal energy also contributes, as temperature gradients drive convective flows that enhance the dynamo effect. The most efficient dynamo processes occur at the boundary between the neutron star's core and inner crust. In this region, superconducting protons interact with the neutron superfluid through magnetic coupling. When the neutron superfluid rotates faster than the proton superconductor, it drags magnetic flux tubes along, generating electric fields that drive additional currents. These currents flow in complex, three-dimensional patterns throughout the magnetar's interior. Unlike simple dipole fields that decrease smoothly with distance, magnetar fields often show multipole structure, with hotspots and field reversals scattered across the surface. This complexity arises from the turbulent nature of the dynamo process itself. Computer simulations of magnetar dynamos reveal a chaotic system where magnetic field lines constantly twist, merge, and reconnect. The magnetic field configuration can change dramatically over timescales of months or years, as the internal dynamo responds to changing conditions. These field reconfigurations often trigger the starquakes and outbursts that make magnetars observable across vast distances. The dynamo also exhibits feedback effects that make its behavior unpredictable. Strong magnetic fields can suppress the very fluid motions that generate them, creating periods of relative calm, followed by sudden bursts of activity. When magnetic stress finally overcomes the suppression, the dynamo can rapidly amplify field strength by orders of magnitude. One of the most remarkable features of the magnetar dynamo is its efficiency. Conventional power generators lose significant energy to heat and friction, but the magnetar's superconducting components eliminate resistance losses entirely. The dynamo can convert nearly 100% of available mechanical energy into magnetic field energy, creating the most efficient electrical generator in the known universe. The dynamo's operation also depends critically on the magnetar's age and thermal evolution. Young magnetars, with core temperatures above 10 billion degrees, support vigorous convective flows that drive powerful dynamo action. As the neutron star cools over thousands of years, the dynamo gradually weakens, leading to the eventual decay of the magnetic field. Recent theoretical work suggests that magnetar dynamos might operate in several distinct modes. During quiet periods, the dynamo maintains a relatively stable field configuration, but when instabilities develop, the system can switch to a highly active mode characterized by rapid field changes and violent outbursts. The magnetar's internal dynamo represents nature's ultimate demonstration of electromagnetic induction. This cosmic generator has been running continuously since the neutron star's formation, converting stellar rotation into magnetic field strength with an efficiency that human technology can only dream of achieving. Understanding this dynamo process could revolutionize our approach to magnetic field generation and energy storage in terrestrial applications. Scattered across a magnetar's surface like cosmic campfires, hotspots glow with temperatures exceeding 50 million degrees, hot enough to fuse any known atomic nuclei instantly. These regions, each smaller than a city but brighter than entire star systems, mark the places where the magnetar's twisted magnetic field lines penetrate the crustal surface. When these hotspots merge or suddenly brighten, they create fireworks visible from billions of light years away. Each hotspot forms where magnetic flux tubes emerge from the magnetar's interior and pierce through the solid crust. The magnetic field strength in these regions can exceed 100 billion Tesla, strong enough to compress atoms into needle-like shapes and polarize the vacuum of space itself. The concentrated magnetic energy heats the crustal material to temperatures where it glows primarily in X-rays and gamma rays. The size of these hotspots ranges from a few miles across to areas comparable to small countries. Despite their relatively tiny size compared to the magnetar's total surface area, individual hotspots can outshine the combined light output of 10,000 suns. The energy density in these regions exceeds anything found in normal stellar atmospheres by factors of millions. Hotspots aren't static features. They evolve and migrate across the magnetar's surface as the internal magnetic field changes configuration. Space-based X-ray telescopes have tracked hotspots, moving at speeds of several miles per hour, following complex paths that reveal the underlying magnetic field structure. Some hotspots appear suddenly during outbursts, while others fade gradually over periods of months or years. The most spectacular events occur when two or more hotspots merge together. The collision between separate magnetic flux systems releases enormous amounts of stored magnetic energy in seconds or minutes. During one such merger, observed on magnetar SGR 1830-0645, the combined hotspot brightened by a factor of 100, briefly becoming one of the brightest X-ray sources in our galaxy. The extreme conditions in hotspots create physics laboratories impossible to duplicate on Earth. The magnetic field strength approaches the quantum critical threshold, where photons can spontaneously split into electron-positron pairs. The thermal energy density reaches values where matter and antimatter creation becomes a continuous process rather than a rare quantum fluctuation. Hotspots also serve as particle accelerators, more powerful than any human-built machine. Charged particles get trapped along magnetic field lines and accelerated to near light speeds by the intense electric fields generated through magnetic reconnection. These relativistic particles create beams of synchrotron radiation that can be detected across intergalactic distances. The temperature profile within a hotspot shows extreme gradients over very short distances. The central regions, where magnetic field lines are most concentrated, reach temperatures approaching 100 million degrees. But just a few miles away, the magnetar's surface temperature drops to the relatively cool value of 10 million degrees. This temperature structure creates convective flows and plasma instabilities that make hotspots dynamic, ever-changing features. Hot plasma rises from the interior while cooler material sinks, creating circulation patterns that redistribute magnetic flux and thermal energy. These convective motions can trigger secondary heating events that cause hotspots to flare unpredictably. The light emission from hotspots provides astronomers with direct observational evidence of the extreme physics operating on magnetar surfaces. The X-ray spectrum shows characteristic features that reveal magnetic field strength, temperature, and the exotic states of matter present in these regions. Polarization measurements confirm that light passing through hotspot atmospheres experiences vacuum, birefringence, and other quantum electrodynamic effects. Recent observations have revealed that some magnetars have hotspots that persist for years or decades, while others show rapidly evolving patterns, with hotspots appearing and disappearing on timescales of days. This diversity suggests that different magnetars may have fundamentally different internal magnetic field configurations. The study of hotspot evolution has become a new frontier in understanding how magnetar magnetic fields evolve over time. Each hotspot represents a window into the magnetar's interior, providing clues about the dynamo processes and magnetic field generation mechanisms operating deep within these cosmic monsters. When hotspots collide, they demonstrate that even the most extreme objects in the universe continue to surprise us with their violent beauty. On December 27, 2004, at 9:05 p.m. Greenwich Mean Time, every gamma-ray detector in the solar system went blind. A magnetar located 50,000 light-years away had just experienced the most violent explosion observed in recorded history. In 1/10 of a second, this city-sized object released more energy than our sun will produce in the next 100,000 years. The explosion began with a crack in the magnetar's crust, barely visible to the naked eye. After years of slowly building magnetic stress, a fault line developed in the crystalline surface material. The initial fracture propagated across thousands of square miles in milliseconds, releasing gravitational binding energy equivalent to a magnitude 10 earthquake. But the mechanical energy represented only the beginning. When the crystal lattice cracked, it severed magnetic field lines that had been anchored in the crust for years. These field lines contained enormous amounts of stored magnetic energy, enough to power human civilization for billions of years. All of this energy got released in a matter of seconds. The liberated magnetic energy instantly heated the fracture zone to temperatures exceeding 10 billion degrees. At these temperatures, any form of matter gets converted to plasma, a state where atomic nuclei and electrons exist as separate, highly energetic particles. The plasma expanded from the magnetar's surface at 20% of light speed, carrying magnetic field lines along in a phenomenon called magnetic field line inflation. The expanding fireball created a blister of superheated plasma extending thousands of miles above the magnetar's surface. Within this fireball, the magnetic field strength remained intense enough to continue affecting fundamental physics. Photons split into electron-positron pairs, which then annihilated back into gamma rays in a cascade of matter and energy conversion. The explosion's intensity overwhelmed the magnetar's own gravitational field in the affected region. For several minutes, the expanding plasma achieved escape velocity, meaning that some of the neutron star's own material got blasted into space. This represents one of the few known mechanisms capable of removing matter from a neutron star's surface. The gamma-ray burst produced by this explosion saturated detectors on spacecraft throughout the solar system. The International Space Station's instruments recorded radiation levels 100 times higher than normal background. Even spacecraft on the far side of the solar system detected the event clearly. If this magnetar had been located just 10 light-years away instead of 50,000, the radiation dose would have been lethal to any life on Earth. But the explosion's effects extended far beyond just gamma rays. The violent magnetic field reconfiguration launched a shockwave through the magnetar's magnetosphere, the region of space dominated by its magnetic field. This shockwave accelerated charged particles to near light speeds, creating a burst of radio waves that arrived at Earth several minutes after the initial gamma-ray flash. The explosion also permanently altered the magnetar's rotation. The sudden redistribution of mass across the surface changed the neutron star's moment of inertia enough to speed up its rotation by a measurable amount. Precision timing measurements revealed that the magnetar's rotation period decreased by several milliseconds, ATA, a tiny change that nonetheless represents enormous energy transfer. Seismic waves from the explosion propagated through the magnetar's interior at speeds approaching significant fractions of light speed. When these waves reflected off the boundary between the crust and core, they triggered secondary fractures and additional energy releases. The magnetar continued producing smaller outbursts for months after the main explosion. The December 27th event provided the first direct measurement of the energy stored in magnetar magnetic fields. The total energy release exceeded 10 to the 44th joules. Sun will produce more energy than our Sun will produce over its entire main sequence lifetime. This confirmed theoretical predictions about the enormous energy reservoirs contained within twisted magnetic field configurations. Most remarkably, the explosion was detected by its effects on Earth's upper atmosphere. The intense gamma radiation ionized atmospheric particles on the night side of our planet, temporarily disrupting radio communications and creating artificial aurora displays. The magnetar had reached across 50,000 light-years of space to remind us of the incredible violence lurking in the cosmic deep. When a magnetar's crust finally surrenders to magnetic stress, the resulting starquake makes terrestrial earthquakes look like gentle tremors. These cosmic seismic events propagate through matter so dense that earthquake waves travel at significant fractions of light speed, carrying energy equivalent to the detonation of trillion megaton hydrogen bombs. The December 27th, 2004 starquake from SGR 1806-20 was detected by seismic instruments on Earth, despite occurring 50,000 light-years away. The magnetar's crust exists in a state of perpetual stress that would instantly shatter any terrestrial material. Magnetic field lines, anchored in the crystalline surface, create twisting forces equivalent to supporting the weight of Mount Everest on every square inch. As the internal magnetic field evolves over months and years, this stress accumulates until it exceeds even the incredible strength of neutronium crystal. The breaking point arrives without warning. A microscopic flaw in the crystal structure, TA, perhaps a single misaligned nucleus, suddenly propagates into a macroscopic fracture. The crack spreads across the magnetar's surface at speeds approaching light itself, following the weakest paths through the crystalline lattice like cosmic lightning. Unlike earthquakes on Earth, which release primarily mechanical energy, magnetar starquakes liberate enormous amounts of magnetic energy stored in twisted field lines. When the crystal cracks, magnetic flux tubes that have been held in place for years suddenly snap back to lower energy configurations. The magnetic energy release exceeds the mechanical energy by factors of thousands. The starquake generates several different types of seismic waves, each carrying information about the magnetar's internal structure. Primary waves compress and decompress the neutron matter as they propagate, traveling through the core at speeds exceeding 100,000 miles per second. Secondary waves create shearing motions that can only propagate through solid material, allowing scientists to map the boundary between the solid crust and liquid core. The most exotic seismic waves are unique to neutron stars. Magnetic waves propagate along field lines at speeds determined by the magnetic tension and plasma density. These magnetoseismic oscillations can carry energy between different regions of the magnetar, sometimes triggering secondary fractures far from the original earthquake. Surface waves on a magnetar behave unlike anything seen on terrestrial planets. The extreme gravitational field confines these waves to a thin layer just above the crust, where they can circle the entire neutron star in milliseconds. When surface waves from different parts of the starquake meet and interfere, they create standing wave patterns that make the entire magnetar ring like a cosmic bell. The ringing frequency depends on the magnetar's internal structure and composition. By analyzing the quasi-periodic oscillations detected in X-ray emissions following major starquakes, astronomers can determine the thickness of the crust, the density profile of the core, and even the equation of state governing matter at nuclear densities. Some starquakes trigger cascading failures that reshape the magnetar's entire surface. The initial fracture relieves stress in one region, but transfers it to neighboring areas. This can create a domino effect where secondary fractures propagate around the magnetar's circumference, ultimately cracking large portions of the crust within minutes. The largest starquakes can actually change the magnetar's shape. The sudden redistribution of crustal material alters the neutron star's moment of inertia, causing permanent changes in its rotation period. The December 27th event decreased the magnetar's rotation period by several milliseconds, a tiny change that nonetheless represents the movement of quadrillions of tons of matter. Starquakes also launch blast waves through the magnetar's magnetosphere that can be detected across intergalactic distances. These shock fronts accelerate charged particles to near light speeds, creating the brief but intense gamma-ray bursts that first revealed magnetars to human observation. Recent computer simulations suggest that the most powerful starquakes might even trigger changes in the magnetar's core. Seismic waves reflecting off the crust-core boundary could disrupt the delicate balance of quantum fluids in the interior, potentially triggering core oscillations that persist for months. The magnetar has turned seismic activity into a weapon capable of shaking the entire galaxy with its cosmic rage. Light itself becomes trapped inside a magnetar's field, forced to follow invisible highways of magnetic force like a cosmic subway system. Photons that would normally travel in straight lines find themselves bent, twisted, and channeled along magnetic field lines, in defiance of everything we thought we knew about the behavior of light. In the magnetar's domain, even the fastest thing in the universe must bow to the supreme power of magnetism. The trapping occurs because the magnetar's field strength exceeds the quantum critical threshold, where electromagnetic radiation begins interacting strongly with the magnetic field itself. Photons acquire an effective mass in this environment, making them behave more like particles than pure energy. They get deflected by magnetic forces, and can even orbit around regions of especially intense field strength. X-rays and gamma rays, emitted from the magnetar's hotspots, cannot escape directly into space. Instead, they become confined to narrow channels along magnetic field lines, creating beams of radiation that sweep across the cosmos like lighthouse beams. These photon highways extend thousands of miles above the magnetar's surface, guiding radiation along predetermined paths regardless of its initial direction. The magnetic confinement creates a phenomenon called photon splitting, where high-energy gamma rays spontaneously divide into two or more lower-energy photons when traveling through the intense field. This process, impossible under normal conditions, becomes commonplace near magnetars. A single gamma ray can cascade into dozens of X-rays, each following slightly different magnetic field lines. The reverse process also occurs through magnetic photon merging. Multiple X-rays traveling along the same field line can combine into single gamma rays with enormous energy. The magnetar's field acts like a cosmic particle accelerator, concentrating electromagnetic energy into increasingly powerful packages. These trapped photons create their own magnetic pressure that can affect the field structure itself. When enough radiation gets confined along particular field lines, the photon pressure can actually reshape the magnetic field, creating feedback loops between light and magnetism. The magnetar becomes a self-modifying electromagnetic system where light influences the very forces that control it. The most spectacular manifestation of photon trapping occurs during magnetar outbursts. When hotspots suddenly brighten, they flood nearby magnetic field lines with intense radiation. The trapped photons create pressure waves that propagate along field lines at light speed, carrying energy to distant parts of the magnetosphere, where it gets released as secondary bursts. Polarization effects in the trapped light provide astronomers with detailed maps of the magnetar's field structure. As photons travel along curved magnetic field lines, their polarization rotates in predictable ways. By measuring these polarization changes, scientists can reconstruct the three-dimensional topology of the magnetic field, extending thousands of miles into space. The photon trapping also creates unique spectral signatures that distinguish magnetars from other high-energy sources. Absorption features appear at specific energies corresponding to quantum transitions in the magnetized vacuum. These cyclotron resonance features shift in energy as the magnetic field strength changes, providing direct measurements of field evolution over time. Some of the trapped photons become so tightly bound to magnetic field lines that they orbit the magnetar multiple times before escaping. These photons create a kind of electromagnetic atmosphere around the neutron star, storing energy that can be released suddenly during magnetic reconnection events. The trapping efficiency depends strongly on photon energy and magnetic field strength. Low-energy radio waves pass through the field relatively unaffected, while high-energy gamma rays become completely confined. This creates an energy-dependent escape probability that shapes the observed radiation spectrum. Recent theoretical work suggests that photon trapping might be responsible for some of the quasi-periodic oscillations observed from magnetars. As trapped radiation builds up along field lines, it can trigger instabilities that release energy in regular pulses, creating the rhythmic signals that reveal so much about magnetar physics. The magnetar has transformed light from a free-traveling wave into a captive servant, forced to follow the twisted pathways of magnetic dominance. In the twisted space around a magnetar, the fundamental rules governing light and matter break down spectacularly. High-energy photons that should be indivisible packets of pure energy suddenly split into pairs of particles and antiparticles, creating matter from nothing more than electromagnetic radiation. This process, called pair production, transforms the magnetar's surroundings into a cosmic laboratory, where the equivalence of mass and energy becomes a continuous, observable phenomenon. The splitting occurs when photon energies exceed the rest mass energy of electron-positron pairs, about 511,000 electron volts per particle. On Earth, this process requires particle accelerators and extreme conditions. Near a magnetar, it happens automatically to any gamma ray with sufficient energy. The intense magnetic field provides the momentum transfer needed to convert pure energy into matter. When a gamma ray splits, it creates an electron moving in one direction and a positron moving in the opposite direction. Both particles immediately become trapped by the magnetar's magnetic field, spiraling along field lines in tight helical paths. The magnetic force confines them to cyclotron orbits with radii smaller than atomic nuclei, creating a dense plasma of matter and antimatter particles. This pair plasma exhibits properties unlike any material found elsewhere in the universe. Electrons and positrons coexist in close proximity without immediately annihilating because the magnetic field keeps them separated in space. They spiral along parallel paths, creating electric currents that generate additional magnetic fields through electromagnetic induction. The population of pair particles becomes so dense that they begin affecting the propagation of additional photons through the region. The plasma creates an effective opacity that can completely block the escape of high-energy radiation from certain parts of the magnetar's magnetosphere. This photon pair feedback creates a self-regulating system where increased radiation leads to increased pair production, which then suppresses further radiation. The splitting process also works in reverse through pair annihilation. When electrons and positrons finally collide, they convert back into pure energy in the form of gamma rays. But the intense magnetic field affects even this fundamental process, causing the annihilation photons to emerge with preferred directions and polarizations determined by the field geometry. The energy spectrum of split photons reveals detailed information about the magnetic field structure. Photons splitting in regions of higher field strength produce pairs with different energy distributions than those splitting in weaker fields. By analyzing the observed pair production rates, astronomers can map field strength variations across the magnetar's surface and magnetosphere. Cascade processes make the splitting phenomenon even more complex. The positrons created by photon splitting can collide with thermal electrons in the magnetar's atmosphere, producing additional gamma rays that then split into more pairs. This creates electromagnetic cascades, where a single high-energy photon can ultimately produce hundreds or thousands of particle pairs. The magnetic field also affects the threshold energy required for pair production. In extremely strong fields, the quantum vacuum itself becomes unstable, allowing pair creation at lower photon energies than normally possible. This vacuum breakdown represents the ultimate expression of quantum electrodynamics under extreme conditions. The spatial distribution of pair production creates distinct zones around the magnetar. Close to the surface, where magnetic fields are strongest, virtually all high-energy photons split immediately upon emission. Further out, where fields weaken, only the most energetic gamma rays undergo splitting. This creates a layered structure in the magnetosphere with different physical properties at different altitudes. Time-dependent pair production can create oscillations in the magnetar's observable brightness. As the pair density builds up in certain regions, it suppresses photon escape, causing the observed flux to decrease. When magnetic reconnection events suddenly clear out the pair plasma, brightness surges as trapped radiation escapes. Recent observations have detected the characteristic signatures of pair production in magnetar spectra, confirming theoretical predictions about this exotic process. The detection of annihilation features and cyclotron emission from pair particles provides direct evidence that quantum electrodynamics operates as predicted even under the most extreme conditions imaginable. The magnetar has created a realm where light transforms into matter, as routinely as water transforms into ice. 3 miles beneath a magnetar's surface, in the transition zone between the solid crust and liquid core, matter exists in a state that defies every category known to materials science. Here, atomic nuclei stretch and merge into exotic configurations, while electrons flow like liquid metal through the gaps between them. This nuclear pasta layer represents one of the strangest phases of matter in the observable universe, where the boundary between solid and liquid becomes meaningless. The pasta forms because gravity and nuclear forces reach a delicate balance in this region. Above this zone, nuclei maintain their individual identities despite extreme neutron enrichment. Below it, nuclei merge completely into uniform nuclear fluid. But in the pasta layer itself, nuclei adopt intermediate configurations that maximize their binding energy under the competing influences of surface tension and Coulomb repulsion. Gnocchi phase nuclei cluster into spherical droplets separated by regions of free neutron gas. Each droplet contains hundreds of nucleons arranged in a dense, neutron-rich configuration that would be completely unstable under normal conditions. The droplets float in the neutron gas like cosmic ravioli, occasionally merging or splitting as conditions change. As density increases deeper in the pasta layer, gnocchi give way to spaghetti phase structures. Nuclei elongate into rod-like configurations that extend for miles through the neutron star's interior. These nuclear spaghetti strands can carry electric currents like superconducting wires, potentially contributing to the magnetar's enormous magnetic field generation. The transition to lasagna phase occurs where rod-like nuclei begin connecting into sheets. These nuclear membranes separate regions of neutron-rich material from regions of pure neutron gas, creating a layered structure that resembles cosmic geological strata. The sheets can be incredibly thin, just a few nucleons thick, while extending for miles in the other dimensions. In the deepest pasta regions, the lasagna phase inverts to form anti-lasagna, where sheets of neutron gas separate regions of nuclear matter. Finally, anti-spaghetti and anti-gnocchi phases create increasingly exotic topologies before transitioning to the uniform nuclear fluid of the core. The mechanical properties of nuclear pasta exceed anything achievable with conventional materials. Individual pasta strands can support tensions equivalent to the breaking strength of neutron star crusts, while maintaining flexibility that allows them to bend and flex under changing magnetic stresses. This combination of strength and flexibility makes pasta crucial for understanding how magnetar crusts respond to magnetic field evolution. Electric currents flow through the pasta structures with essentially zero resistance. The nuclear matter acts as a superconductor at the extreme temperatures and densities found in neutron star interiors. These superconducting pasta strands can carry enormous electrical currents that persist for millions of years, potentially explaining how magnetars maintain their intense magnetic fields over such long timescales. The pasta's response to magnetic fields creates unique mechanical properties. Magnetic flux tubes can thread through the spaces between pasta structures, creating a complex interaction between nuclear forces and electromagnetic forces. When magnetic stresses become too large, pasta strands can suddenly rearrange, releasing energy that propagates through the neutron star as seismic waves. Thermal properties in the pasta layer differ dramatically from both the crust above and the core below. Heat transport occurs primarily through electron conduction along pasta strands, creating highly directional thermal conductivity. This anisotropic heat flow affects how the magnetar cools over time and may influence the stability of magnetic field configurations. Recent computer simulations suggest that pasta structures can undergo phase transitions that release enormous amounts of energy. When conditions change slightly, spaghetti can suddenly transform to lasagna or gnocchi phases, liberating nuclear binding energy that heats the surrounding material to billions of degrees. The pasta layer also affects neutrino emission from the neutron star interior. Neutrinos produced by nuclear reactions in the core must travel through the pasta structures to escape, and the complex geometry can trap or redirect these ghostly particles in unexpected ways. Understanding nuclear pasta represents one of the greatest challenges in neutron star physics, requiring computational models that can handle the complex many-body interactions between thousands of nucleons under extreme conditions. The magnetar has cooked up a cosmic meal that would challenge the appetite of the universe itself. At the very heart of a magnetar, 9 miles below the exotic pasta layers, quantum mechanics creates whirlpools of neutron fluid that spin with the mathematical precision of cosmic tornadoes. These quantum vortices represent one of the most ordered structures in the universe, where millions of microscopic whirlpools align in perfect hexagonal arrays like a cosmic honeycomb made of pure quantum mechanics. The vortices form because neutrons in the magnetar's core exist as a superfluid, a quantum mechanical state where the entire fluid behaves as a single, coherent quantum system. Unlike ordinary fluids that can rotate smoothly at any rate, superfluids can only rotate in discrete, quantized units. Each vortex carries exactly one quantum unit of circulation, making them the atomic building blocks of rotation in neutron star cores. Individual quantum vortices are incredibly thin, just a few times the size of atomic nuclei, but they extend straight through the entire core like cosmic needles threading through the neutron star's heart. The vortex cores contain essentially no neutron matter, creating tubes of suppressed density that persist as long as the magnetar continues rotating. The number of vortices required to account for a magnetar's rotation defies imagination. A neutron star spinning once every few seconds needs roughly 10 to the 18th vortices threading through its core. These quantum tornadoes organize themselves into triangular lattices with spacing determined by the rotation rate and superfluid density. But magnetar vortices don't exist in isolation. They interact strongly with the magnetic flux tubes that thread through the superconducting proton component of the core. When a quantum vortex encounters a magnetic flux tube, they can link together like cosmic chains, creating combined structures that carry both rotational circulation and magnetic flux. These linked vortex flux systems exhibit collective behavior that affects the entire magnetar. When groups of linked vortices suddenly rearrange or relocate, they can transfer angular momentum between different fluid components, causing observable changes in the magnetar's rotation rate. This vortex dynamics may explain the sudden spin-up events observed from some magnetars during outbursts. The quantum vortices also affect how the magnetar responds to external perturbations. During starquakes, seismic waves propagating through the core can set vortex lattices into collective oscillation modes. These vortex waves can store and transport energy throughout the core, potentially triggering delayed energy releases that occur long after the initial disturbance. Temperature plays a crucial role in vortex behavior. At the extreme temperatures found in young magnetar cores, tens of billions of degrees, thermal fluctuations can cause vortices to move more freely through the superfluid. As the magnetar cools over thousands of years, vortices become increasingly pinned in place by impurities or interactions with the crystal lattice structure. The magnetic field threading through the core affects vortex dynamics in complex ways. Strong magnetic forces can distort the normally straight vortex lines, causing them to bow and curve in response to magnetic pressure. In regions where magnetic field strength varies rapidly, vortices can even fragment into loops or more complex topological structures. Computer simulations of magnetar cores reveal that vortex dynamics can become chaotic under certain conditions. Random thermal fluctuations or magnetic field changes can trigger avalanche-like vortex rearrangements, where thousands of vortices suddenly move in coordinated fashion. These quantum avalanches might be responsible for some of the unpredictable timing irregularities observed from magnetars. The interaction between quantum vortices and the exotic matter phases in the core creates additional complexity. If strange quarks or other exotic particles exist in the magnetar's center, they form their own superfluid components with distinct vortex structures. The resulting multi-component superfluid system can support entirely new types of vortex interactions and collective modes. Recent theoretical work suggests that vortex motion in magnetar cores might generate its own magnetic fields through electromagnetic induction. As superconducting flux tubes move with the vortices, they create electric currents that contribute to the overall magnetic field structure. This vortex-driven magnetism could provide an additional mechanism for magnetic field generation and evolution. The quantum vortices represent nature's ultimate demonstration of quantum mechanics, operating on macroscopic scales, where individual quantum states affect the behavior of objects containing more mass than our Sunday. In the crushing depths of a magnetar's core, protons undergo a transformation that makes them the most perfect electrical conductors in the known universe. Unlike terrestrial superconductors that require cooling to near absolute zero, magnetar protons achieve zero electrical resistance at temperatures exceeding 50 million degrees while supporting magnetic fields that would instantly destroy any human-made superconductor. The superconducting transition occurs when protons get compressed to densities several times higher than atomic nuclei. Under these extreme conditions, protons begin forming Cooper pairs, quantum mechanically bound pairs that can move through the surrounding matter without any energy loss. But these aren't ordinary Cooper pairs like those found in terrestrial superconductors. The binding energy between protons becomes so strong that superconductivity persists at temperatures that would vaporize planets. The mechanism behind this high-temperature superconductivity remains one of the most fascinating puzzles in condensed matter physics. In normal superconductors, electrons pair up through interactions with crystal lattice vibrations. But in magnetar cores, protons pair through direct nuclear interactions mediated by the exchange of virtual mesons, particles that exist only briefly as quantum fluctuations. These proton-Cooper pairs exhibit properties that push the boundaries of quantum mechanics. Each pair behaves as a single quantum entity that can exist in multiple locations simultaneously through quantum superposition. Millions of pairs can occupy the same quantum state, creating a macroscopic quantum system where individual particle behavior determines the properties of stellar mass objects. The superconducting protons create current loops that can persist for millions of years without decay. These persistent currents generate the enormous magnetic fields that define magnetars, carrying electrical currents that exceed the output of entire power grids. A single cubic centimeter of superconducting proton matter can carry enough current to power a major city indefinitely. The current density in these superconducting loops approaches theoretical limits imposed by quantum mechanics. At maximum current density, the kinetic energy of Cooper pairs equals their pairing energy, representing the absolute limit of superconducting performance. Magnetars operate perilously close to this limit, existing in a state where any small perturbation could trigger catastrophic current redistribution. Magnetic flux in the superconducting core gets organized into quantized units called flux quanta. Each quantum carries exactly one fundamental unit of magnetic flux, and the total magnetic field results from millions of these flux quanta threading through the superconducting medium. The flux quanta behave like microscopic magnetic tornadoes, carrying concentrated magnetic field in thin tubes just nanometers wide. The interaction between superconducting protons and superfluid neutrons creates one of the most complex quantum many-body systems imaginable. Proton vortices, or whirlpools in the superconducting component, can link with neutron vortices to form composite structures that carry both magnetic flux and rotational circulation. These linked vortices can move collectively through the core, transferring energy and angular momentum between different fluid components. Phase transitions in the superconducting state can trigger sudden energy releases that power magnetar outbursts. When local conditions change slightly, regions of the core can transition between different superconducting phases, each with distinct magnetic properties. These transitions release binding energy that heats the surrounding matter to billions of degrees. The superconducting state also exhibits remarkable stability against external perturbations. Seismic waves from starquakes can propagate through the core without significantly affecting the superconducting current patterns. This stability helps explain how magnetars maintain their intense magnetic fields even during violent surface eruptions. Temperature gradients in the core create regions where superconductivity exists in different phases. Near the core center, where temperatures are highest, protons may exist in a weak coupling, superconducting state. Toward the edges, where temperatures are lower, strong coupling superconductivity dominates, creating spatial variations in magnetic field generation and current carrying capacity. Recent theoretical calculations suggest that magnetar cores might support multiple types of superconducting phases simultaneously. Different proton pairing mechanisms could operate in different regions, creating a complex patchwork of superconducting domains with varying properties and magnetic field generation capabilities. The magnetar's core represents the ultimate expression of superconductivity, where quantum mechanics operates on astronomical scales to create the universe's most powerful electromagnets. At the deepest levels of a magnetar's core, where pressure exceeds 100 billion pounds per square inch, normal matter may cease to exist entirely. In its place lies strange matter, a soup of fundamental particles containing strange quarks that existed only during the first microseconds after the Big Bang. This exotic material, if it exists, would be more stable than any form of ordinary matter and could potentially convert everything it touches into more strange matter. Strange quarks represent the third member of the quark family, alongside the up and down quarks that compose ordinary protons and neutrons. Under normal conditions, strange quarks decay rapidly into lighter particles, making them impossible to study in terrestrial laboratories. But the extreme pressures in magnetar cores might stabilize strange quarks, allowing them to exist indefinitely as components of exotic matter. The transition to strange matter would occur at the magnetar's very center, where pressures become so extreme that individual neutrons and protons lose their identity. Instead of being confined within discrete particles, quarks become free to roam throughout a large volume, creating a quark soup where strange quarks mix freely with up and down quarks. Strange quark matter exhibits properties unlike anything found elsewhere in the universe. It conducts electricity with zero resistance like a superconductor, but also flows like a superfluid with zero viscosity. The combination creates a material that can support enormous electrical currents while flowing through spaces smaller than atomic nuclei without losing energy. The density of strange matter exceeds that of normal nuclear matter by factors of 2 to 3. A sugar cube of strange quark matter would weigh as much as several mountain ranges. This ultra-high density means that strange matter contains more binding energy per particle than any other known form of matter, making it potentially the most stable configuration possible for bulk matter. If strange matter exists in magnetar cores, it could fundamentally alter our understanding of neutron star physics. Strange quarks carry electric charge, allowing strange matter to participate directly in electromagnetic processes. The magnetic fields generated by currents in strange matter might exceed those possible with normal superconducting protons, potentially explaining the extreme field strengths observed in magnetars. The boundary between normal nuclear matter and strange matter would represent one of the most dramatic phase transitions imaginable. Crossing this boundary would involve the complete reorganization of matter at the most fundamental level, with quarks changing their confinement from individual particles to collective behavior across macroscopic volumes. Color superconductivity adds another layer of exotic physics to strange matter. Just as electrons can form Cooper pairs in normal superconductors, quarks can pair up through their color charge, SAS, the quantum property that governs the strong nuclear force. These quark-Cooper pairs would create superconducting behavior unlike anything observed in conventional materials. The temperature deep in strange matter regions could reach hundreds of billions of degrees, hot enough to create thermal populations of every known fundamental particle. At these temperatures, the distinction between matter and energy becomes blurred, with particles constantly converting between different types through thermal fluctuations. Strange matter might also explain some of the most violent magnetar outbursts. Phase transitions between different types of quark matter could release enormous amounts of energy, potentially powering the gamma-ray bursts that make magnetars detectable across billions of light-years. The conversion of normal matter to strange matter would liberate binding energy exceeding that of nuclear fusion. The stability of strange matter raises profound questions about the ultimate fate of magnetars. If strange matter is indeed more stable than normal matter, it might slowly convert the entire neutron star core through a process analogous to crystallization. This strange matter conversion could alter the magnetar's magnetic field, rotation, and energy output over geological timescales. Recent astronomical observations have searched for signatures of strange matter in neutron star spectra and timing data. While definitive evidence remains elusive, some anomalous observations might be explained by the presence of strange quark cores in the most massive neutron stars. The possibility that magnetars harbor strange matter represents one of the most speculative yet intriguing frontiers in modern astrophysics, where the laws of particle physics meet the extreme conditions of stellar evolution. Threading through a magnetar's interior and extending thousands of miles into space, magnetic field lines twist and coil like cosmic DNA, storing energy densities that approach the theoretical limits allowed by the laws of physics. These invisible highways of electromagnetic force contain more energy than our sun will produce in its entire 10 billion year lifetime, compressed into structures thinner than human hair, yet stronger than neutron star crusts. Each magnetic field line begins and ends at the magnetar's surface, following complex three-dimensional paths that twist through the neutron star's interior before emerging at distant points on the surface. Unlike the simple dipole field lines of Earth, magnetar field lines form intricate knots and braids that can take thousands of years to untangle naturally. The energy storage occurs because magnetic field lines behave like elastic bands under tension. When field lines get twisted or stretched beyond their equilibrium configuration, they store energy in the form of magnetic tension and pressure. The amount of energy stored depends on how far the field lines deviate from their lowest energy state, 10T, and in magnetars, this deviation can be enormous. Computer simulations reveal that magnetar field lines can become twisted into configurations resembling cosmic pretzels, with individual field lines making dozens of complete rotations before connecting back to the surface. Each twist stores additional magnetic energy, building up enormous energy reservoirs that can persist for thousands of years before being released catastrophically. The total energy stored in a magnetar's twisted magnetic field can exceed 10 to the 46 joules, more energy than our sun contains in its entire nuclear fuel supply. This energy exists purely in the form of electromagnetic field configuration, representing one of the most concentrated energy storage systems in the known universe. But storing this much energy creates inherent instabilities. Magnetic field lines under extreme tension constantly seek lower energy configurations through a process called magnetic reconnection. When highly twisted field lines encounter each other, they can suddenly snap and reconnect in simpler configurations, releasing enormous amounts of stored energy in the process. The reconnection process happens at the microscopic level, but affects the entire magnetar. When field lines reconnect, they accelerate charged particles to near light speeds and heat plasma to billions of degrees. The energy release can propagate through the magnetosphere as shock waves that ultimately power the gamma-ray bursts observed from magnetars. The field line energy storage also affects the magnetar's rotation. As field lines twist due to differential rotation between the crust and core, they create magnetic torques that can transfer angular momentum between different parts of the neutron star. This magnetic coupling explains how surface eruptions can suddenly change the magnetar's rotation rate. Deep inside the magnetar, field lines interact with the various exotic matter phases in complex ways. Superconducting protons pin magnetic flux in place, preventing field lines from moving freely through the core. When magnetic stresses overcome this pinning, flux tubes can suddenly jump to new positions, triggering seismic events that propagate through the entire neutron star. The magnetic energy density in some regions approaches the rest mass energy density of matter itself. At these extreme values, the magnetic field begins affecting the geometry of spacetime, creating gravitational effects that contribute measurably to the magnetar's total mass. The stored magnetic energy literally adds weight to the neutron star. Field line topology changes over time as the magnetar evolves. Young magnetars with highly twisted field configurations gradually relax towards simpler states, releasing energy through a series of outbursts and eruptions. This magnetic evolution explains why magnetar activity tends to decrease over timescales of thousands of years. Some theoretical models suggest that magnetar field lines might store enough energy to completely unbind the neutron star if released simultaneously. This represents a theoretical upper limit on magnetic energy storage. Beyond this point, the magnetic forces would overcome gravity and tear the magnetar apart. Recent observations have begun mapping the three-dimensional structure of magnetar field lines through polarization measurements and spectral analysis. These observations reveal field configurations of extraordinary complexity that challenge our understanding of how such extreme magnetic structures can remain stable. The magnetar's field lines represent the ultimate expression of electromagnetic energy storage on cosmic scales. At the magnetar's magnetic poles, where field lines converge with mathematical precision, nature has constructed the universe's most lethal particle accelerators. These polar cap regions, each smaller than Manhattan, but more powerful than the largest human-built accelerators, launch death beams of relativistic particles that can sterilize planets from distances of light years. When these cosmic weapons activate, they create the most intense concentration of electromagnetic energy possible without forming a black hole. The polar caps mark the points where the magnetar's internal magnetic field lines emerge from the surface and extend into space. Unlike Earth's gentle magnetic poles, magnetar polar regions experience field strengths exceeding 1 billion Tesla, strong enough to compress atoms into needle-like shapes and tear electrons from their orbital shells through pure magnetic force. The extreme field curvature at the poles creates electric fields so intense they spontaneously create matter from the vacuum. Virtual particle pairs that normally exist only as quantum fluctuations become real electrons and positrons when exposed to the polar electric fields. This pair creation process happens continuously, feeding a steady supply of charged particles into the magnetar's particle acceleration system. These newborn particles immediately get trapped by the converging magnetic field lines and accelerated to incredible speeds. The electric fields at magnetar poles can reach values exceeding 10 to the 13th volts per meter, millions of times stronger than the fields in terrestrial particle accelerators. Particles gain energy at rates that would accelerate them to near light speeds in distances measured in inches. The acceleration process creates two distinct types of death beams. Primary beams consist of electrons and positrons, accelerated directly by the polar electric fields. These particles follow tightly curved trajectories as they spiral around magnetic field lines, emitting intense synchrotron radiation that appears as X-rays and gamma rays to distant observers. Secondary beams form when high-energy particles from the primary beams collide with the magnetar's atmosphere or surface. These collisions create cascades of additional particles that get accelerated by the same polar fields. The cascade process can amplify the initial particle flux by factors of thousands, creating dense beams of relativistic matter. The particle beams carry enormous amounts of energy, equivalent to the output of entire power plants concentrated into beams narrower than city blocks. When these beams strike matter, they deposit their energy so rapidly that any material instantly vaporizes into plasma. A magnetar's death beam could sterilize Earth's entire biosphere in seconds if directed toward our planet. The beams also carry away angular momentum from the magnetar, causing it to gradually slow down over time. This magnetic braking process explains why magnetars rotate more slowly than typical neutron stars, despite their young ages. The energy and angular momentum carried away by the death beams represents a significant drain on the magnetar's rotational energy reservoir. Atmospheric effects near the polar caps create additional exotic physics. The intense radiation pressure from accelerated particles can levitate matter above the magnetar's surface, creating thin atmospheres of iron and heavier elements held in place by radiation forces rather than gravity. These levitated atmospheres glow with temperatures exceeding 10 million degrees. The death beams can extend far beyond the magnetar's immediate vicinity. Relativistic particles in the beams can travel for light years before losing significant energy, carrying the magnetar's influence to distant parts of the galaxy. Planets unfortunate enough to lie in the path of these beams would experience radiation doses lethal to any conceivable form of life. Temporal variations in the polar cap activity create the pulsed emissions that allow astronomers to detect magnetars across vast distances. As the magnetar rotates, its death beams sweep across space like cosmic lighthouses, creating regular pulses of high-energy radiation with clockwork precision. Recent observations have revealed that some magnetars have multiple polar caps, suggesting more complex magnetic field structures than simple dipoles. These multipolar configurations can create multiple death beams, pointing in different directions, multiplying the magnetar's destructive potential. The polar caps represent the magnetar's ultimate weapon, cosmic death rays, powered by the fundamental forces of electromagnetism and quantum mechanics. Inside a magnetar, temperature varies more dramatically over shorter distances than anywhere else in the observable universe. The core blazes at 100 billion degrees, any atomic, hot enough to photodisintegrate any atomic nucleus instantly, while regions just a few miles away maintain temperatures of merely 10 million degrees. These extreme thermal gradients create convective flows and heat transport mechanisms that operate at the very limits of physical possibility. The temperature extremes result from the competing effects of magnetic field decay heating and neutrino cooling. Deep in the core, the slow unwinding of twisted magnetic field lines deposits enormous amounts of energy, heating the neutron fluid to temperatures exceeding those found in stellar cores. But neutrino emission carries away energy at such prodigious rates that the core temperature can drop by orders of magnitude over distances measured in miles. The magnetic heating process works through a phenomenon called ohmic dissipation, where electrical currents flowing through regions of finite resistance convert electromagnetic energy into thermal energy. Even in the magnetar's superconducting core, tiny amounts of resistance exist at the boundaries between different phases of matter, creating localized heating that can raise temperatures by billions of degrees. Neutrino cooling operates through multiple channels that compete with magnetic heating. Beta decay processes convert neutrons to protons while emitting neutrinos that escape at light speed, carrying away thermal energy. Modified Urca processes involve multiple particles and can cool the neutron star core more rapidly than any other known mechanism. The competition between heating and cooling creates thermal runaway zones where small changes in conditions can trigger dramatic temperature increases. When magnetic heating slightly exceeds neutrino cooling in a region, the temperature rise enhances the heating rate while reducing cooling efficiency, creating positive feedback loops that can heat matter to hundreds of billions of degrees in minutes. Heat transport through the magnetar's interior occurs primarily through electron thermal conduction, but the extreme magnetic fields dramatically alter this process. Electrons can only move freely along magnetic field lines, creating highly anisotropic thermal conductivity. Heat flows readily along field lines, but barely at all perpendicular to them, creating complex temperature patterns that follow the magnetic field geometry. The thermal gradients drive convective instabilities that mix different layers of the magnetar's interior. Hot matter rises while cool matter sinks, but the magnetic field constrains these motions to occur only along field lines. This creates columnar convection cells that extend through the entire neutron star, mixing exotic matter phases in ways that affect the magnetic field generation and evolution. Phase transitions triggered by temperature changes can release additional energy that amplifies the thermal gradients. When hot matter from the core encounters cooler regions, it can trigger transitions between different nuclear phases or superconducting states, liberating binding energy that further heats the surrounding material. The surface temperature of a magnetar reflects the complex thermal processes occurring in its interior. Hot spots mark regions where heat transport from the interior creates surface temperatures exceeding 50 million degrees, while other areas remain relatively cool at 10 million degrees. These temperature variations create the X-ray emission patterns that allow astronomers to study magnetar physics. Thermal waves propagating through the magnetar's interior can create delayed responses to internal heating events. When magnetic reconnection releases energy deep in the core, the resulting thermal pulse can take months or years to reach the surface, creating the long-duration brightenings observed from some magnetars. The extreme temperature gradients also affect the stability of different matter phases. Regions that would normally support exotic quark matter might revert to nuclear matter when heated above critical temperatures, creating dynamic boundaries between different phases that shift as thermal conditions change. Recent computer simulations suggest that the temperature distribution in magnetar cores might be inherently chaotic, with small changes in initial conditions leading to dramatically different thermal evolution. This thermal chaos could explain the unpredictable timing and intensity of magnetar outbursts. Magnetic field lines threading through regions of extreme temperature gradients can develop thermomagnetic instabilities that trigger sudden energy releases. These instabilities might be responsible for some of the shorter duration bursts observed from magnetars, where thermal and magnetic effects combine to create explosive energy liberation. The magnetar's interior represents a cosmic furnace, where temperature differences that would power civilizations exist across distances smaller than cities. On December 27, 2004, SGR 1806-20 demonstrated that tectonic activity in the universe can exceed anything imaginable on Earth. In 1/10 of a second, crustal fractures propagated across the magnetar's surface at 20% of light speed, releasing seismic energy equivalent to a magnitude 32 earthquake. The event redefined our understanding of what geological processes can achieve under extreme conditions. The magnetar's crust exists under stresses that dwarf anything experienced by terrestrial tectonic plates. Magnetic forces equivalent to supporting the weight of Mount Everest on every square inch constantly twist and distort the crystalline surface material. Unlike Earth's plates that move inches per year, magnetar crustal segments can suddenly shift by miles in milliseconds when magnetic stresses finally overcome the crust's incredible strength. The propagation speed of crustal fractures approaches relativistic velocities because the neutron star crust has properties unlike any terrestrial material. The speed of sound in neutronium crystal exceeds 30,000 miles per second, roughly 10% of light speed. Seismic waves traveling at these velocities can circle the entire magnetar in less than a second, creating global crustal disruptions from localized fractures. The fracture mechanics operate on principles that push solid-state physics to its limits. When the crystalline lattice finally fails under extreme magnetic stress, the crack doesn't propagate gradually like fractures in normal materials. Instead, entire regions of crust can fail simultaneously across areas larger than continents, releasing gravitational binding energy equivalent to the detonation of quadrillions of hydrogen bombs. The magnetic field threading through the crust creates additional complexity in the fracture process. When crustal segments move, they drag magnetic field lines along with them, storing additional energy in twisted field configurations. This magnetic coupling can accelerate crustal motion beyond what gravitational forces alone could achieve, creating the near light speed displacements observed during major starquakes. The December 27th event caused measurable changes in the magnetar's shape and rotation. The sudden redistribution of crustal material altered the neutron star's moment of inertia enough to change its rotation period by several milliseconds. This represents the movement of quadrillions of tons of matter in a fraction of a second, demonstrating energy transfer rates that exceed the power output of entire galaxies. Crustal plate motion on magnetars doesn't follow the gradual drift patterns seen on Earth. Instead, plates can suddenly teleport to new positions when magnetic forces overcome static friction. The transition from stationary to relativistic motion happens essentially instantaneously, creating shock waves that propagate through the magnetar's interior at significant fractions of light speed. The magnetic coupling between crust and core creates feedback effects that can amplify crustal motion. When surface plates move, they alter the magnetic field configuration throughout the neutron star. These field changes can trigger additional crustal failures in distant regions, creating cascading starquakes that reshape the entire surface in minutes. The energy released during high-speed crustal motion gets converted into multiple forms. Kinetic energy of moving crustal segments creates seismic waves that heat the fractured regions to billions of degrees. Magnetic energy, liberated by field line reconnection, launches plasma fireballs above the surface. Gravitational energy release triggers oscillations in the neutron star's interior that can persist for months. Recent computer simulations reveal that magnetar crustal motion exhibits chaotic behavior, where small changes in initial stress configurations can lead to dramatically different fracture patterns. This chaotic nature might explain why magnetar outbursts appear random and unpredictable, despite being governed by deterministic physical laws. The high-speed motion creates novel forms of seismic waves that have no terrestrial analogues. Magnetic waves, coupled to mechanical vibrations, can propagate through the crust at speeds approaching light itself, carrying information about crustal motion throughout the entire neutron star in milliseconds. Time-lapse observations of magnetar surfaces during major outbursts show crustal segments appearing to vanish and reappear in new locations as they move faster than telescopes can track. These disappearing acts represent real physical motion of solid matter at relativistic speeds rather than any illusion or instrumental effect. The magnetar has transformed plate tectonics into a relativistic phenomenon, where continents can relocate at speeds that approach the cosmic speed limit. Within every magnetar, an epic thermal battle rages between the blazing hot interior and the cooling surface, fought with weapons of neutrino radiation and magnetic field energy across temperature differences that span factors of thousands. This cosmic thermal war determines how long magnetars remain active, how their magnetic fields evolve, and when they finally surrender to the cold embrace of space. The war begins immediately after the neutron star's formation, when the core temperature reaches 100 billion degrees, while the surface cools rapidly through photon emission to space. The temperature gradient between core and surface creates driving forces for heat transport that exceed anything found in normal stellar interiors by factors of millions. The core fights to retain its thermal energy through multiple defensive mechanisms. Superconducting protons and superfluid neutrons have extremely high heat capacity, allowing them to store enormous amounts of thermal energy without dramatic temperature changes. The magnetic field acts like thermal insulation, constraining heat flow to occur only along field lines and creating complex patterns of hot and cold regions. But the surface launches its own thermal assault through neutrino emission processes that can strip energy from the core faster than any other cooling mechanism in nature. Modified Urca reactions convert neutrons to protons while emitting neutrinos that escape at light speed, carrying away binding energy that exceeds the thermal energy content of entire stars. The magnetic field itself becomes both a weapon and a casualty in this thermal war. Magnetic field decay deposits enormous amounts of energy into the core, heating it far above the temperatures that neutrino cooling alone could maintain. But the same heating process that feeds the thermal battle gradually weakens the magnetic field, ultimately determining the duration of the magnetar's active phase. Heat transport through the magnetar's interior creates complex temperature patterns that shift and evolve over thousands of years. Thermal waves propagating outward from the core can take centuries to reach the surface, creating delayed heating events that cause sudden changes in surface temperature long after the initial core heating occurs. The nuclear pasta layers serve as thermal battlegrounds, where different cooling mechanisms compete for dominance. Electron thermal conduction along pasta strands can rapidly transport heat in some directions, while insulating against heat flow in others. This anisotropic heat transport creates temperature gradients that can trigger convective instabilities and further complicate the thermal evolution. Phase transitions throughout the magnetar's interior can suddenly tip the balance in the thermal war. When hot matter undergoes transitions between different superconducting phases or nuclear configurations, it can release binding energy that temporarily overwhelms neutrino cooling. These phase transition heating events create thermal pulses that propagate through the neutron star like thermal shock waves. The surface temperature reflects the cumulative outcome of all interior thermal processes. Young magnetars with core temperatures exceeding 50 billion degrees maintain surface temperatures of 30 million degrees, hot enough to emit primarily in X-rays. As the thermal war gradually favors cooling over heating, surface temperatures drop, and the magnetar fades from observational detectability. Magnetic reconnection events create sudden heating pulses that can briefly reverse the cooling trend. When twisted magnetic field lines snap and reconnect, they deposit enormous amounts of energy into localized regions, creating temperature spikes that can exceed the core temperature for brief periods. These thermal bombs explode throughout the magnetar's interior, adding unpredictability to the thermal evolution. The thermal war also affects the magnetar's magnetic field stability. Temperature changes alter the superconducting properties of the core, potentially triggering sudden redistributions of electrical currents that power the magnetic field. Hot regions might lose superconductivity entirely, causing magnetic flux to relocate and creating the field reconfigurations observed during magnetar outbursts. Computer simulations of magnetar thermal evolution reveal that the cooling war follows predictable patterns for the first few thousand years, but becomes increasingly chaotic as thermal and magnetic instabilities accumulate. Small differences in initial conditions can lead to dramatically different thermal histories, making long-term predictions impossible. The ultimate victor in this thermal war is predetermined entropy, and the second law of thermodynamics ensure that cooling must eventually triumph over heating. But the battle can rage for 10,000 years before the magnetar finally succumbs to thermal death. In the twisted magnetosphere surrounding a magnetar, magnetic field lines carry out a cosmic dance of connection and destruction that releases more energy than entire galaxies produce through stellar fusion. When highly stressed field lines encounter each other and suddenly reconnect in simpler configurations, they unleash explosive energy releases that can be detected across billions of light years. These magnetic reconnection events represent the most efficient energy conversion process known in the universe. The reconnection process begins when oppositely directed magnetic field lines approach each other in the magnetar's complex field geometry. Unlike the gentle reconnection events that create aurora on Earth, magnetar reconnection involves field lines carrying energy densities that exceed the rest mass energy of matter. When such field lines meet, they don't just reconnect, they explode. The collision occurs at microscopic scales, but triggers consequences that affect the entire magnetar system. At the reconnection point, magnetic field lines snap like cosmic rubber bands, accelerating charged particles to near light speeds and heating plasma to temperatures exceeding 100 billion degrees. The energy conversion efficiency approaches 100%, making reconnection the ultimate expression of electromagnetic energy liberation. The process happens faster than human comprehension can follow. Reconnection events complete themselves in microseconds, but during that brief time, they can release more energy than our sun produces in millions of years. The speed of energy release exceeds the power output of entire galactic cores, concentrated into regions smaller than cities. Multiple reconnection events can trigger cascading energy releases that reshape the magnetar's entire magnetosphere. When one reconnection event occurs, it sends shockwaves through the surrounding magnetic field that can trigger additional reconnections throughout the system. These magnetic avalanches can convert significant fractions of the magnetar's total magnetic energy into kinetic energy and heat in matters of seconds. The charged particles accelerated by reconnection create the most intense particle beams in the known universe. Electrons and positrons gain energies exceeding those achieved in the most powerful terrestrial particle accelerators, but the magnetar accelerates trillions of particles simultaneously, rather than the handful produced by human machines. These accelerated particles emit synchrotron radiation as they spiral around magnetic field lines, creating the intense X-ray and gamma-ray emission that makes magnetars detectable across cosmological distances. The radiation pressure becomes so intense that it can actually affect the dynamics of the reconnection process itself, creating feedback loops between electromagnetic energy and particle acceleration. The reconnection events also launch plasma bubbles that expand away from the magnetar at significant fractions of light speed. These magnetic plasmoids carry enormous amounts of energy and can persist for hours or days as they travel through the magnetar's magnetosphere. When plasmoids eventually dissipate, they deposit their energy into the surrounding medium, heating it to temperatures where exotic physics becomes important. The three-dimensional structure of magnetar reconnection defies simple description. Unlike two-dimensional reconnection models that assume infinite field lines, magnetar reconnection occurs in complex geometries, where field lines can reconnect in multiple locations simultaneously. This creates explosive energy releases that propagate in all directions through the magnetosphere. Recent computer simulations reveal that magnetar reconnection can exhibit turbulent behavior, where energy cascades from large scales to small scales through a hierarchy of increasingly violent interactions. This magnetic turbulence creates power law energy distributions that explain the observed variety of magnetar outburst intensities. The reconnection process also affects the magnetar's rotation through magnetic braking. When field lines reconnect and launch material away from the neutron star, they carry angular momentum with them, causing the magnetar to spin down over time. This magnetic spin down provides another mechanism for converting rotational energy into electromagnetic radiation. Some theoretical models suggest that the largest reconnection events might temporarily overwhelm the magnetar's gravitational field in localized regions. The electromagnetic forces generated during explosive reconnection could exceed gravitational forces, potentially allowing matter to escape from the neutron star's surface, despite its enormous gravitational pull. The magnetic reconnection events in magnetar magnetospheres demonstrate that electromagnetic forces, when concentrated sufficiently, can compete with gravity itself in determining the behavior of stellar mass objects. These cosmic explosions represent the universe's ultimate demonstration of how magnetic fields can store and suddenly release energy on scales that dwarf human comprehension. After 10,000 years of violent outbursts that shake the galaxy, every magnetar faces the same inevitable fate. Its incredible magnetic field begins to fade, its surface cools to darkness, and the cosmic monster gradually transforms into a silent, invisible corpse drifting through space. This death process reveals the ultimate limits of even the most extreme magnetic fields, showing how entropy and the laws of physics eventually triumph over the greatest concentrations of electromagnetic energy in the universe. The dying process begins when the magnetar's core temperature drops below the critical threshold needed to maintain vigorous convective motion. As thermal energy dissipates through neutrino emission, the turbulent flows that help generate and sustain the magnetic field gradually subside. Without these driving motions, the magneto-hydrodynamic dynamo that amplified the field to magnetar strengths slowly winds down. Magnetic field decay accelerates as the superconducting currents in the core begin to encounter increasing resistance. While superconductors normally carry electrical current without energy loss, the extreme current densities in magnetar cores push these materials to their absolute limits. As temperatures drop and the superconducting properties weaken, tiny amounts of resistance appear that allow magnetic energy to dissipate as heat. The decay follows an inexorable, exponential decline, with a characteristic timescale of 10,000 years. During this period, the magnetic field strength drops from 100 trillion times Earth's field to merely 1 billion times Earth's field, still enormous by terrestrial standards, but insufficient to power the violent outbursts that characterize active magnetars. As the magnetic field weakens, the mechanisms that heat the magnetar's surface gradually shut down. Magnetic field line reconnection becomes less energetic and less frequent. The hot spots that once blazed brighter than suns gradually cool and fade. The X-ray emission that made the magnetar visible across the galaxy dims to undetectable levels. The cooling surface temperature drops below the threshold needed to emit X-rays, shifting the magnetar's output to lower energy radiation that becomes increasingly difficult to detect. Within 20,000 years of formation, most magnetars fade below the sensitivity limits of current X-ray telescopes, effectively disappearing from astronomical observation, despite continuing to exist as physical objects. The crustal fractures that created the spectacular starquakes also become less frequent and less violent as magnetic stresses diminish. The crystalline surface, no longer subjected to field strengths that exceed its breaking point, settles into a more stable configuration. The era of global crustal failures and relativistic plate motion comes to an end. Some magnetars may experience brief revivals if they encounter interstellar matter that accretes onto their surfaces. The gravitational energy released by infalling material can temporarily reactivate magnetic heating processes, causing the dead magnetar to flicker back to life for periods ranging from months to centuries. But these revival episodes become increasingly rare as the underlying magnetic field continues its relentless decay. The final stages of magnetar death leave behind objects that closely resemble ordinary neutron stars. The magnetic field, while still strong by terrestrial standards, no longer dominates the physics of the surface and magnetosphere. The neutron star becomes a quiet, slowly cooling ember that will take billions of years to reach thermal equilibrium with the cosmic microwave background. Some theoretical models suggest that magnetar death might not be permanent. If the neutron star later acquires a companion star through stellar capture or binary evolution, matter accreted from the companion could potentially restart the dynamo process and regenerate strong magnetic fields. This recycling mechanism might explain why some old neutron stars exhibit magnetar-like properties. The death of a magnetar also releases its grip on the surrounding interstellar medium. During its active phase, the magnetar's intense radiation pressure and particle winds can clear out cavities in the local gas and dust. As the magnetar fades, these cleared regions begin to refill with interstellar matter, gradually erasing the evidence of the magnetar's former violence. Recent surveys have identified several candidate dead magnetars, neutron stars, with properties suggesting they were once active magnetars, but have now faded below detectability. These ghostly remnants provide glimpses into the final fate awaiting all magnetars, no matter how violent their active phases. The death of a magnetar marks the end of one of nature's most spectacular displays of electromagnetic fury, leaving behind only memories encoded in the structure of the surrounding interstellar medium. In the ultimate cosmic catastrophe, two magnetars spiral toward each other in a death dance that releases more energy than 10,000 supernovas and creates gravitational waves that ripple through the fabric of space-time itself. When these magnetic monsters finally merge, they forge exotic matter that has never existed since the Big Bang, while simultaneously detonating the most powerful explosion possible without creating a black hole. The collision begins millions of years before impact, when gravitational waves slowly drain orbital energy from the binary magnetar system. As the two neutron stars spiral closer together, their magnetic fields begin to interact across the narrowing gap between them. The field interaction creates electromagnetic forces that can exceed the gravitational attraction, causing the final approach to deviate from purely gravitational predictions. During the last seconds before merger, the magnetar's surfaces begin to distort under mutual tidal forces, while their magnetic fields reconnect explosively in the space between them. These pre-merger reconnection events release energy equivalent to major stellar flares, creating a fireworks display that illuminates the cosmic neighborhood with high-energy radiation. The actual collision occurs when the two neutron star surfaces make contact at speeds exceeding 20,000 miles per second. The kinetic energy of the merger instantly converts the contact region into quark plasma heated to trillions of degrees, temperatures that existed only during the first microseconds after the universe began. The magnetic fields of both magnetars, each carrying energy equivalent to stellar masses, undergo catastrophic reconnection during the merger. The combined magnetic energy release creates a blast that can outshine entire galaxies for minutes, launching jets of relativistic plasma that extend across light years of space. These magnetic explosions may be responsible for some of the mysterious fast radio bursts detected by radio telescopes. The collision produces gravitational waves with amplitudes thousands of times larger than those generated by merging black holes. These space-time ripples carry away enormous amounts of energy and angular momentum, causing the newly merged object to lose mass, equivalent to several planets in the form of pure gravitational radiation. The merger remnant depends critically on the total mass of the two colliding magnetars. If the combined mass exceeds about 3 solar masses, the merged object immediately collapses into a black hole, ending the story in a final burst of gravitational waves. But if the mass stays below this threshold, something far more exotic emerges. A successful merger creates a hypermassive magnetar of an object that shouldn't be able to exist according to normal neutron star physics. The enormous rotational energy from the collision temporarily supports masses that would normally collapse into black holes, creating neutron stars that spin hundreds of times per second, while maintaining magnetic fields stronger than anything else in the universe. The hypermassive magnetar's interior contains matter in states that push physics beyond current understanding. Quark matter, strange matter, and possibly even more exotic phases coexist in a rapidly rotating, intensely magnetized environment where the boundaries between different fundamental forces become blurred. The collision also launches massive amounts of neutron-rich material into space at significant fractions of light speed. This ejector undergoes rapid neutron capture processes that forge heavy elements, including gold, platinum, and rare earth metals. A single magnetar merger can produce more precious metals than our Sun will create in its entire lifetime. The electromagnetic signature of the merger creates what astronomers call a kilonova, an explosion that can be seen across billions of light years and lasts for weeks. The radioactive decay of newly synthesized heavy elements powers this long-duration afterglow, which provides direct evidence that neutron star mergers are responsible for much of the universe's supply of elements heavier than iron. The hypermassive remnant can survive for minutes to hours before either stabilizing as an extremely massive neutron star or collapsing into a black hole. During this brief existence, it represents the most extreme concentration of matter, energy, and magnetic field that can exist in our universe. Recent gravitational wave detections have confirmed that neutron star mergers occur regularly throughout the cosmos, suggesting that these ultimate magnetic collisions have been enriching the universe with heavy elements and reshaping space-time since the first stars died billions of years ago. In the far future, when humanity has mastered the fundamental forces of nature, magnetars may become the ultimate weapons in cosmic warfare by stellar-scale cannons capable of sterilizing entire solar systems with focused beams of death radiation. But long before any civilization could hope to weaponize these magnetic monsters, magnetars themselves may already be serving as inadvertent cosmic destroyers, randomly exterminating life across the galaxy with their unpredictable outbursts. The December 27th, 2004 eruption from SGR 1806-20 demonstrated magnetar's potential for mass destruction. From 50,000 light-years away, this single outburst temporarily blinded every gamma-ray detector in our solar system and significantly affected Earth's upper atmosphere. If the same magnetar were located just 10 light-years from Earth, the radiation dose would have caused a mass extinction, rivaling the asteroid impact that killed the dinosaurs. Computer simulations reveal that a major magnetar outburst at galactic distances, typical of nearby star systems, would strip away planetary atmospheres and sterilize any surface-dwelling life within hours. The intense gamma-ray flux would destroy the ozone layer, allowing deadly ultraviolet radiation to reach planetary surfaces for thousands of years afterward. Advanced civilizations might attempt to harness magnetar energy for constructive purposes. The total magnetic energy stored in a single magnetar exceeds humanity's current energy consumption by factors of trillions. A civilization capable of extracting even a tiny fraction of this energy could power interstellar expansion and massive engineering projects that reshape entire solar systems. But magnetars resist all attempts at control or prediction. Their outbursts follow no discernible pattern, making them unsuitable as reliable energy sources. The same unpredictability that makes them dangerous also makes them nearly impossible to exploit safely. Any civilization attempting to approach a magnetar would face the constant risk of sudden annihilation. The magnetic fields around magnetars could theoretically be used to accelerate spacecraft to significant fractions of light speed. Charged particle beams launched from magnetar polar caps already achieve these velocities naturally. A sufficiently advanced civilization might develop technologies to ride these magnetic acceleration fields like cosmic highways. Military applications represent the darkest potential future for magnetar technology. A civilization capable of moving or aiming magnetars could create weapons of unimaginable destructive power. A magnetar positioned in an enemy solar system could eliminate all life on inhabited planets while leaving the planets themselves intact for later colonization. The magnetars themselves may already be inadvertently sterilizing vast regions of the galaxy. Statistical studies suggest that major magnetar outbursts occur frequently enough to periodically irradiate most star systems in our galactic neighborhood. This magnetar sterilization hypothesis might partially explain why we haven't encountered other intelligent civilizations. They keep getting eliminated by random magnetic explosions. Some theoretical models suggest that magnetars could trigger chain reactions in nearby star systems. The intense radiation from magnetar outbursts might destabilize other stellar objects, potentially triggering supernovas or other catastrophic events that amplify the destruction across multiple star systems. Climate change on Earth might be influenced by distant magnetar activity. Major outbursts could affect our planet's atmospheric chemistry in subtle ways that accumulate over geological timescales. Some mass extinction events in Earth's history might correlate with known magnetar locations and estimated outburst times. The search for extraterrestrial intelligence may need to account for magnetar effects when predicting where life could survive long enough to develop advanced civilizations. Star systems located in regions of high magnetar density might be poor candidates for hosting long-lived civilizations, regardless of their other characteristics. Future space exploration will need to monitor magnetar activity and develop protection against sudden outbursts. Deep space missions could be destroyed instantly by unexpected gamma-ray bursts from previously unknown magnetars. As our understanding of magnetars improves, we may discover that these cosmic monsters play fundamental roles in galactic evolution that extend far beyond their individual violent outbursts. They might regulate star formation, influence the distribution of heavy elements, and determine which regions of the galaxy can support stable, long-lived planetary systems. The magnetars represent both the universe's ultimate demonstration of electromagnetic fury and a sobering reminder that cosmic forces beyond human control continue to shape the destiny of life throughout the galaxy.